Welcome everybody. I'm Aldo Di Carlo, the director of Istituto di Struttura della Materia of National Research Council. It's really a pleasure for me to introduce this International Day of Light, and it's a pleasure to welcome the speakers. They are coming from many parts of the world just to witness the importance of the Day of Light. So, as you know, the light is part of our day experience, and we have light from sun, we have light from artificial light. So we use light every day, and we are part of the light experience every day. Today, actually, we will discover other forms of use light or other forms of light that have been used or are used by researchers now in the future. Also, technology will make use of these discover what the scientists will present today. As an institute related to the matter, we are heavily making very use of light and in many characterizations. So I want to say that recently we are involved in the revamping of the synchrotron. We have 3 synchrotron line, and we are part of this project for Electra 2.0. So the light coming from synchrotron is part of our characterization activity. But we use light in laser for characterization and also for fabrication. We use light coming from sun for conversion with the solar cell and other devices. And we are moving also in the context of solar fuel to use light, the electromagnetic radiation, for creating fuel for the next generation energy. So all these parts are very important and makes the activity we are doing. But of course, I mean, this is just a part of the use and experience of light. And today in this marvelous program we will discover use of light in many different contexts from, as I say, from synchrotron to the quantum application. I really thank the speakers for their presence today, and I really like now to open the session and to give the word to Lorenzo Avaldi that will chair the session this morning. Thanks a lot, and have a nice time.
Okay, so good morning to everybody. I'm Lorenzo Avaldi, senior researcher at the Institute of Structural Matter of National Research Council, and I will serve as a chair of both the morning and afternoon section. So we start in the morning section with the first talk given by Alexei Kavokin. Alexei is the director of the International Center for Polaritonics and chair professor at Westlake University, and is an expert of light matter coupling and solid state physics. For the audience, if you like to set a question, comment to the speaker, please use the social channel, and then we will propose the question to the speaker. Please, Alexei.
Hello, everyone. It's a great pleasure and honor to me to take part in this event. And I spent my best years in Italy. Actually, I worked in Rome back in 1997, 98 with Aldo Di Carlo, and then later in the framework of Marie Curie Chair of Excellence with Rodolfo Del Sole at the Physics Department of Tor Vergata. And then later I joined CNR. So for 4 years, I was part of CNR. Then I moved to China. So now I lead a center that is called International Center for Polaritonics in China. And I will now, if I manage to share my screen, I will show you the picture of my Chinese group. I don't know if you can see it now. If screen sharing works. So this is the recent photo taken at some group gathering in China. So in 5 years, we built an international center for polaritonics, world first. And in this center, we study liquid light. And so today I will tell you what liquid light is and how it can be used to make a quantum computer. This is an outline of my talk. I will introduce the main character of this story, exciton polariton, that is a quasi-particle that can be called a quantum of liquid light. And then I will present the concept of qubits based on exciton polaritons, on liquid light. And I will tell you how these qubits are now being experimentally studied, realized, and put together to make quantum networks and quantum simulators. So this is a work in progress. There is no yet ready quantum computer, but you will see that the progress is quite fast, actually. So to start with, what is an exciton polariton? First of all, what is an exciton? An exciton is very similar to a hydrogen atom, but if a hydrogen atom is formed by a proton and an electron, an exciton in a semiconductor is formed by also a positively charged quasi-particle called hole and an electron, that is the electron in the conduction band of the semiconductor. They are bound together by Coulomb attraction, exactly as proton and electron in the hydrogen atom, and they form this hydrogen-like particle that is much larger in size than a hydrogen atom. The typical size of an exciton is 100 angstrom. And also the binding is much smaller. So the Rydberg constant for an exciton is maybe 100 times or 1,000 times smaller than for the hydrogen atom. But also the main difference is that these excitons, they do not live forever, because an electron and the hole can disappear. They recombine, and the energy of exciton is released, and it can be released in the form of a photon. So if the exciton recombines, a photon is emitted. But if we are still in the semiconductor or in a semiconductor structure, this emitted photon can be reabsorbed and it can create the exciton again. And then this exciton can again emit a photon, and the photon can be again reabsorbed, and so on and so on. So from the point of view of quantum mechanics, you can never tell before you do the measurement. You can never know where and when you have an exciton and where and when you have a photon. Only when you do the measurement, you find this entity in a state of exciton or in a state of photon. Before that, it exists in a quantum superposition of a matter quasi-particle, that is exciton, and a quantum of light, that is photon. And that is why the properties of these exciton polaritons, they are inherited both from light and from matter. They combine properties of light and matter. So as matter particles, they can interact with each other, but as light, they can propagate with a high speed, they can have polarization, phase, they can be described by wave equations, basically, like any light. So at the end of the last century, it was proposed that exciton polaritons, being bosons, bosonic quasi-particles, they can form bosonic condensates. And Bose-Einstein condensates are such states that that are composed by many particles, but all these particles are in the same quantum state. So they have the same energy, the same wavelength. And it was first theoretically proposed, and then it was realized in a variety of structures. And interestingly, it was also realized at room temperature. I underline that before that, in 20th century, the phenomenon of Bose-Einstein condensation was only observed in atomic gases at ultra-low temperatures of the order of nanokelvin. But here in semiconductor structures, we can have a Bose-Einstein condensation at room temperature. And this is very interesting because this coherent many-body effect, it can be brought to the everyday life. It is no more exotic, it is no more a matter of just research in laboratories, but it can be used potentially. So how can it be used? The first idea was to make low threshold lasers, and indeed lasers were done, but the niche for applications is not so large of polariton lasers. However, when working on lasers, we discovered that actually this is a fantastic system to play with wave functions. Because polariton condensates, they can be characterized by many body wave functions, and these wave functions can be observed in optical experiments. As it is shown on this slide, this is an experimental work where in a trap, in a parabolic trap, you see more than 10 quantum confined energy levels. All of them are occupied by the condensate of exciton polaritons. And by doing so-called tomography, spectral tomography measurement, you can visualize a wave function of the condensate at every level, every energy level, from the first to the seventh, as you see here, and even higher. So you can see it and you can engineer it. You can change the shape of a trap, and then your wave function would change. So you can put it in a shape that you need. And this, the coherence of this state, it is preserved over macroscopic time. Even if each individual exciton polariton, it lives not so long time, maybe a few tenths of picoseconds, and then it disappears by going away from the structure, tunneling through the mirrors. The whole condensate, it can live forever. Some particles go away, but some particles come in if you have pumping, and the condensate persists, and it keeps coherent over all time of its life, and it can live potentially infinitely, provided that it is constantly pumped. So this offers a tremendous opportunity to use this very stable, coherent states for quantum information processing. And first works, well, during the last decade, were devoted to the creation of arrays of polariton condensates. They were realized by etching of semiconductor structures or by localization of polariton condensates in optical traps. There are different methods, and actually they were very successful. So here on this slide, you see an array of 1024 condensates, polariton condensates, and they are created by optical pumping, but non-resonant. So the optical pumping just creates electron-hole pairs, which are not excitons and not coherent. And then themselves, they self-organize, they form excitons. Excitons start emit light, and light is being reabsorbed. So you have these polaritons. And in each point, each bright point of this picture, you have maybe 20,000, 30,000 exciton polaritons sitting in the same quantum state, sharing the same quantum state. And what is even more interesting, this array of condensates can be fully phase-locked on a time scale of 100 picoseconds, so 10 to minus 10 seconds. These self-organized states, they find some arrangement so that the phase relations between every two condensates is fixed, and it does not change with time. So it can be experimentally measured, and you have plenty of time to measure it because it exists forever. Until you keep pumping the system, it doesn't change. So it was realized that the specific phase configuration that is chosen by the system minimizes the so-called XY Hamiltonian, which is interaction Hamiltonian of two-dimensional spins. And this theta is an angle between spin number I and spin number I plus 1. So two vectors, there is an angle theta between them, and the Hamiltonian, it contains cosine of this angle. So it is a very complex Hamiltonian if you have 1,000 terms in it, 1,000 condensates. But actually more than 1,000 terms, of course, because you have 1,000 condensates, but each of them can interact with many others. But still, the system finds the ground state of this Hamiltonian on a time scale of 10 to minus 10 seconds. And this is a tremendous opportunity for the realization of a simulator. So a device that solves one specific problem, but solves it much faster than any classical computer or supercomputer. So that was a proposal of 2017. And I should emphasize that while it is very interesting, it is not yet a quantum computer, and it is not yet anything quantum because there is no qubits here. A condensate is not a qubit. But a qubit can be prepared from the condensate. And for this, we need to exploit the superfluidity of polarity on condensates, superfluidity of liquid light. This effect, very similar to the superfluidity of liquid helium, it was experimentally observed back in 2008-2009, initially at low temperatures, but now it is also observed in perovskite, for example, microcavities at room temperature. And the effect of superfluidity is basically the coherent effect. This superfluid liquid does not see obstacles. It moves without friction, without viscosity, and it can form, for example, vortices that exist forever, circular currents that exist forever, because liquid moves without any resistance, without any friction. And this is what can be used in qubits. The idea is very similar to what is realized already with superconductors. Also in the superconductors, you can have a current that propagates forever without any friction, without any resistivity. And the same with the superfluid. The only difference is that a superfluid current, it does not carry electric charge. Our exciton polaritons are electrically neutral. But if you put them on a ring, they can be characterized by a phase. And the phase, this macroscopic phase of the whole ensemble of tens of thousands of particles, it must be a continuous function of the coordinate. So if you go around the circle, it must change by an integer number of 2 pi. And this is very similar to what happens in a superconductor. So in a superconductor, they pass a magnetic flux, and if this flux is equal to half quantum, then realization of clockwise and anti-clockwise currents that enhance the magnetic flux to the full quantum or suppress it to zero. So the realization of these two currents has equal probabilities. And the system, if there is some Josephson junction that mixes currents, it has two new eigenstates, which are superpositions of clockwise and anti-clockwise currents. So on these superpositions, they build superconducting qubits, which are very, very popular now and used in Google quantum computer, in IBM quantum computer, in Chinese quantum computers. And the same can be done conceptually the same with the superfluid qubits. Just instead of magnetic field, we use so-called weak link that pins a dark soliton. And a dark soliton is characterized by a phase jump by pi over 2. So the phase on the circuit would change by pi, by pi here in the point of defect, and then it should change by other pi or minus pi when you go around the circuit. And these two solutions are degenerate, but this degeneracy can be lifted because of this weak link. And again, you have two states which are superposition states of two superfluid currents, clockwise and anti-clockwise, and you can make a qubit. So to make the long story short, one can say that in a superconducting qubit, in every qubit, something must be quantized. Yes, this is a quantum object, so something must be quantized. But in a superconducting qubit, it is the magnetic flux that is quantized. But in a superfluid qubit, it is a topological charge. Topological charge tells you how many times the phase changes by 2 pi when you go around the circuit. So quantization of topological charge is at the heart of these polarity qubits, which have been proposed by our group in China in 2021. Then the realization came very soon because ring condensates, ring polarity condensates have been already studied by then. They are realized in micropillars and they demonstrate persistent superfluid currents with different topological charges. Here you see the currents with charges +1 and -1 that manifest themselves in interferometry spectra of this condensate. So the phase, how it changes as a function of coordinate, it can be deduced from interferometry measurements. And this technique is well established. Now, when it came to realization of qubits, of course, a lot of work had to be done to optimize the trap where this condensate would be formed. And the most flexible are optical traps. So here we have studied elliptical traps that are optically induced. And the energy spectrum of the condensate in this elliptical trap, it consists of many discrete energy levels, but we choose two of them that lie closely. And on these two states, we realize the qubit. How to control it? The idea came from the group of Pavlos Lagoudakis in Skoltech. They control the state of a qubit by rotating the trap. If you have an elliptical trap and you manage to rotate it, then you make realization of a current propagating in the same direction as the direction of rotation preferential. So how to rotate it? By optical methods. You create a trap by a superposition of two excitation beams, and both of them are Laguerre-Gaussian beams that carry orbital momentum, +1 and -1, and they are slightly detuned in energy. Due to this detuning in frequency, in energy, the trap, the potential, the combined potential that is created by these two laser beams, it rotates. And you can control the speed of this rotation by controlling the detuning between these two laser beams. So you can rotate it clockwise, you can rotate it anti-clockwise. And this group, they observed that the probability of generation of clockwise and anti-clockwise superfluid currents is exactly the same if the trap does not rotate, so 50-50. But if it rotates, so preferentially you start generating the currents that propagate in the direction of rotation. And then really you can achieve 100% of, in 100% of cases, or almost 100% of cases, the superfluid current would go, for example, clockwise. But if you change the speed of rotation to the opposite, then you will have 100% of anti-clockwise currents. So this is a switch. You can control the state of your qubit. Now, if you created it already, you initialize it. You can also swap the direction of rotation by sending a pi pulse of light. Pi means it is a half period of full oscillation between clockwise and anti-clockwise direction. So in this case, it is about 100 picosecond duration of a pulse. And Mark Assmann in Dortmund, he observed in this paper the switching between current of one direction to current of the other direction, passing by some so-called dipole states. And this basically, this is the logic gate. This is the logic gate, a single qubit logic gate that can be used in future polariton quantum computers. Now, to build a quantum computer, we need single qubit gates and double qubit gates. So the next step was to realize double qubit traps. So two elliptical traps together. And the energy spectrum of two elliptical traps together, it shows also many states, but we choose 4 that form this group that stay together. And on these 4, we build our 2-qubit gate. And the main problem here, how to read out the information of this qubit. So it is done optically. Light that comes out of this unknown state of every qubit, it passes through the phase mask. SLM, special light modulator, creates a phase mask that sets a basis in which you measure your state. Then, if the state of the condensate coincides with the state of the phase mask, then after the phase mask, you have a Gaussian beam that passes through the optical fiber, a single mode optical fiber. Then it comes to the photomultiplier, and you have some signal. You say 1, signal equal to 1. But if the state of the condensate does not coincide with the state of the phase mask, then you have not a Gaussian beam, but maybe Laguerre-Gaussian, and it doesn't go through the single mode fiber, and you have a signal equal to 0 on the photomultiplier. And when you have 2 qubits, you do separately these measurements for the first one and second one, and you change the basis for them. So usually there are 2 bases chosen for one and 2 bases chosen for the second one, and altogether this experimental setup allows you to feel a 4x4 matrix that is the measurement matrix of double qubit. So first experiments like this have been realized in Russian Quantum Center by Roman Cherbunin, and this work is now in progress also in China. So altogether, if it works, it would give us a polariton quantum computer. And how it operates is shown on this slide. There is a lot of text here. I'm not sure I have time to read all this, but basically the idea is that you have non-resonant optical pumping that just creates electron-hole pairs, and it creates also the network, the potential on a planar microcavity. So with light, you just draw the potential. And in this potential, your polariton condensates start forming. So initially, when the first exciton falls into the set of polariton modes, it does not go to one specific mode, because one specific mode would have some percentage of exciton and some percentage of light. Initially, you have no light; you just have an exciton. So it will be necessarily distributed as a superposition between many states. So then this superposition, it can die, the exciton can disappear, but it can also survive, and it can be amplified by new excitons, more excitons coming to the system. This is a stimulated scattering process that is responsible for creation of exciton polariton condensates. So the condensate grows, and it is in a superposition of 2 or several states in a trap. And this is the initialization of our system, multi-qubit system, that is prepared in some specific quantum state that we need. So the condensates interact with each other, usually nearest neighbors. So far, we cannot couple next nearest neighbors, but we are working on that. And due to these interactions, already the system starts performing some calculation. but you can also control it by light pulses of chosen duration. So you can switch quantum states of individual condensates, and you can affect also condensate interaction. And this is how you realize logic gates. The most challenging is, of course, 2-qubit logic gate like C0 or ISWAP, and this is so far the main goal of our experimental research, to realize this gate. Then at some stage, this system, it becomes classical. It is projected to the classical basis. For example, that the basis actually you can choose with also with special light modulator. You set the basis in which you detect the system, to which you project the system. So the system, this quantum superposition, it is projected to the classical basis at the stage of readout. But what is very important is that after the readout, the system survives. It just stays in that state, and it can stay forever until you switch off pumping. And this is very important because this is memory. So the polariton system is very powerful because it combines the possibility of doing quantum operations, quantum simulations, but also once it becomes projected to the classical basis, then you keep in memory this the result, the solution, and you can keep it for a long time, as much as you need. So that was, of course, the concept. The realization, it is now being done. So here are 4 coupled qubits already realized, and here are 22. So again, a tremendous breakthrough in the group of Pavlos Lagodakis in Skoltech to appear in Nature Communications very soon. He managed to couple 22 polariton qubits on a hexagonal lattice. He, by single-shot interferometry measurements, he demonstrated the stochastic behavior. So each time the measurement was projecting the system to some classical state that is shown by this red and blue arrows showing the direction of vortices or circular currents, clockwise or anti-clockwise. And each realization was different from the other. So clearly he had a superposition state initially, but when he was doing the measurement, each time it was projected to one of possible classical realizations. And then one can, of course, study statistics of this system and see what happens when you change initial conditions, etc. So this system is not a quantum computer. There is no logic gates here, but there are 22 coherently coupled qubits. So this is a simulator. This is a quantum simulator. And actually what it simulates an Ising Hamiltonian, because every vortex can be mapped to a spin that has 2 classical projections up or down that correspond to clockwise and anti-clockwise direction of current, of polariton current. And with this system, you can find a minimum of quantum Ising Hamiltonian. So for 22 coupled qubits, it is still within reach of classical supercomputers. The threshold is somewhere at the level of 25. And if we would go beyond 25, then this system would hopefully demonstrate the quantum advantage. So it would find the minimum of a Hamiltonian that is impossible in a reasonable time to solve with a classical supercomputer. So then we are looking further. We are looking for universal quantum computer and realization of simple algorithms. So the programmable quantum computer, and the simplest one is Deutsch algorithm that doesn't require many qubits, just a few. And our collaborators, they predicted the fidelity that is rather high of these measurements, but this is yet to be implemented experimentally. And well, other polariton quantum protocols, they're being studied theoretically, They're being modeled on classical computers, supercomputers, and they wait for their experimental realization. So this brings me to my conclusions. I wanted to convince you that liquid light is very, very promising for quantum information processing. And this is because actually the system is very flexible. First of all, these condensates and superfluids, you can realize them at room temperature in a variety of systems. So this is a great advantage with respect to superconducting qubits. Then you can control them fully optically. You can draw a network, set a network of coupled qubits optically. You do not need to make new and new structures, new and new processors for different networks. You just change a code of the special light modulator that creates this optical potential. And everything actually is done optically. Readout is optical. Switching, gate operations are fully optical, which is convenient. And it ensures that everything is ultra fast and losses are small because light is very coherent compared to matter, to electronics. So this is a semiconductor-based technology. Semiconductor-based technologies are well developed. So this constitutes very significant advantages. But of course, this platform for quantum computation is in its infancy so far. We cannot yet compete with big platforms like superconducting qubits, just for the simple reason that they had 30 years of development, and we just started. Still now there are 6 laboratories all over the world, also in Italy, by the way. There is a very nice group in Lecce with Daniele Sanvito working on this topic, who study static polariton qubits and different their realizations actually. So double and quadruple optical traps for polariton condensates are under study and being optimized. And as you saw here, Ising simulators based on polariton qubits are being developed. The Chinese consortium that I represent as a Chinese professor now, it goes in four different directions, developing different material systems for quantum polaritonics. And there are actually best Chinese universities involved in this research. So we cautiously hope that some significant progress will be achieved very soon. For more information, we recently published this review paper in Nature Physics, and where we talk about polariton condensates for classical and quantum computing. And I would be also very glad to answer your questions. So thank you very much for your attention. Sorry, Lorenzo, your microphone is muted.
Okay, sorry. Thank you very much, Alexei, for your interest in talking, introducing this fascinating world of liquid computing. I don't see questions, so I have just a very basic question from my point of view. You said that you have got now for the simulator about 22 qubits, and then the next step should be 25. From an experimental point of view, what are the challenges to go to 25? Because for me, 22, 25 are not so far.
Yes, exactly. Actually, the challenge is not that big because these qubits that they are created by this special light modulator, and already we had more than 1,000 coupled condensates created with the same modulator. The difference is that condensates are not qubits. Qubit is a ring, and the condensate is a point. And it is a little bit more difficult to create a ring, and it is a bit larger. So 22, it came just because on the space that we could illuminate by a laser beam, we could place 22. But now with a slightly larger spot of light, carefully programming this special light modulator, we can go to a larger amount of of qubits. So I believe 25 is not a problem at all, and it can be 30, can be 40, can be 50. Cannot promise 1,000 right now, but a few tens is definitely possible.
Okay, thank you. So far no question. So thank you again, Alexei, and we can move to the next speaker. That is Massimo Altarelli. Is Massimo there?
Yes, I'm here.
Okay.
Can you hear me?
Oh yes, I can hear.
Very
So
good.
Massimo Altarelli has been the managing director of the European X-FILE project since 2005, and now is a senior scientist at the Center for Free Electron Laser at the Max Planck Institute for Structure and Dynamics in Hamburg. And she's an expert in condensed matter physics. And today he will talk about the accelerator-based UV and X-ray light sources, past, present, and brilliant future. So please, Massimo.
Yes, I am
Uploading.
trying to upload my presentation. The smaller file. They say the file is too big. But can I just put the thing on the screen and share the screen? Wouldn't that be easier?
I think so. Just ask to the people from the web.
Share screen. Okay, that's the way to do it. Okay, share screen. Fine. And then select the window. Okay, I think you're seeing now.
Not yet. Okay.
Yes.
Okay.
You see?
Very good.
Very good, maybe. But okay, I will try to make it in presentation mode. Okay. Is it okay now?
Yeah, it's okay.
Oh, it's okay. Okay, so first of all, let me thank the organizers of this beautiful symposium for giving me this chance to be present and to tell you something about the story of accelerator-based UV and X-ray sources, which is a rather long story, but is still going on, and it will be going on with great news for a while. So what I plan to do is to say very few words about why UV and X-ray radiation is very useful for scientific research, which probably all of you know very well. Then I will mention some words about the history of synchronous radiation that started in 1947, actually, 76 years ago, and track a little bit the evolution until, to these days, the extremely brilliant source, or EBS, at the ESRF in Grenoble. And then I will also talk about the wish to have shorter and shorter pulses with sufficient intensity to perform experiments, and therefore talk about the development of free electron lasers. And then also for the free electron lasers, describe how in the future new concepts like FEL oscillators and Wakefield accelerators, laser Wakefield accelerators, are pushing further the possibilities of these sources. So let me say, first of all, the use of X-ray and ultraviolet radiation in science could take easily a full lecture. Let me tell you very simply that, the X-ray scattering or X-ray diffraction is used to locate the position of atoms in a structure, because the cross-section for X-ray scattering is proportional to the square of the Fourier transform of the charge. There are not going to be too many equations in this talk, don't worry, this is just one. But, a most important example of what you can do with X-ray diffraction to determine the atomic structure of systems was given by this historic, experiment by Watson and Crick and Maurice Wilkins and Rosalind Franklin that used X-ray diffraction to determine the structure of the double helix of DNA and to sort of launch the whole field of molecular genetics. Now, if you look at another application of UV and soft X-ray radiation, which is photoemission spectroscopy, the photoelectric effect has been very well known. In 1905, Einstein applied the quantum theory to the photoelectric effect, basically by measuring not only the energy, but also the angle of emission of electrons ejected from a surface with the use of UV radiation. You can reconstruct, in the technique that is called ARPES, angle resolved photoemission, you can basically map the band structure of solids, including, in some cases, even the spin structure. So, and this has been applied as a primary tool for the investigation of electronic structure of solids, which has been, of course, has a very long and very fruitful history. Now, as I said, the whole thing, the use of accelerators as light sources started in 1947, where the five gentlemen that you see on this picture at the General Electric labs in Schenectady, New York, were having this sort of toy synchrotron that you see on the left on the table. And if you look to the picture on the right, you see that there is a flash of light coming out of the 70 millions of electron volt, a flash of blue light. The picture was in black and white, but it was blue light towards a short wavelength. And this was the first observation of synchrotron radiation. Now, in reality, the development of synchrotron radiation owes a lot to the fact that our colleagues in nuclear and subnuclear physics were building bigger and bigger accelerators to pursue their goals. And in fact, large accelerators are extraordinary sources of radiation. The reason is very simple. We know from classical electromagnetism that what induces the generation of radiation is the acceleration of charges. And you have to think that in an accelerator that is a few hundred meters long and has an energy, a relativistic energy, in the sense that the energy exceeds by a large amount the rest energy of the electron, your electrons are moving, you know, when they are at the top of this picture, at the top of the ring, they are moving to the right with the speed of light, and of the order of 1 microsecond later, they are moving in the opposite direction with minus the speed of light. So if you imagine traveling at the speed of light in one direction and in 1 microsecond reverting in the opposite direction, you can imagine what kind of acceleration that is. And because of the fact that the energy is relativistic, so the rest mass is a small energy compared to the energy of the electrons, it turns out that this radiation is highly collimated, has polarization properties, it has a very broad bandwidth, and it has a radiation power that grows with the fourth power of the energy divided by the square of the radius of curvature. So you can build facilities which have really tremendous amount of radiation for your scientific use. This is a cartoon that shows, you know, a conceptual picture of a synchronous radiation source where you see the electrons orbiting in the ring and passing through the bending magnets. They emit photons that reach several experimental stations on their way. Now, this had, as I said, this very modest start in the General Electric lab, but it was an immense success story. And there are now more than 50 synchronous radiation sources worldwide. And they have been, work on synchronous radiation sources has been winning 6 Nobel Prizes, essentially for chemistry, essentially for structural biology. One fundamental progress in this goal was the invention of the insertion devices of the undulators, which you again see in this cartoon. Here, instead of having, using the radiation from the bending magnets, you create a sort of many bands along a straight section of the machine, so that you untangle the radius of curvature of the ring from the radius of curvature of the band. And also, since it takes a finite time, instead of having a very broad band, you now have a more monochromatic radiation, because it takes you have in your field of view as an observer for longer time the radiation. So the 6 Nobel Prizes, as you see, are between 1988 and 2012, and they compensate the discoveries which are very important for biology and all sorts of things, and they were really would not have been. This research could not have been performed without the synchrotron sources. Now, it turns out that, you can think, you would like to have a more and more intense light sources, but what does intensity mean? There are many ways to define intensity. One way is to use the photon flux, which is the number of photons per unit fine and unit surface. But it turns out that a much more valuable figure of merit when you require tight focusing or high spatial and angular resolution is what is called spectral brilliance or brightness, which is basically the number of photons per unit time divided essentially by the photon phase space. That is to say, to have all the photons concentrated with a source point as compact as possible and with a divergence as small as possible, of course, with the limitations of the uncertainty principle and the diffraction limit of classical optics. So generally speaking, this photon phase space volume turns out to be a convolution of the electron phase space volume, how well the accelerator physicists managed to control the shape and divergence of the electron beam, and the photon phase space volume, which is always bigger than the diffraction limit because of the Heisenberg principle. So the idea is to, let's see now. I don't seem to be able to move my slides anymore. Let me see if I can go back. Nope. I should probably restart the show. Let's see if I can do that. Okay. Okay. All right. Now we are back in business, apparently. So, concerning the brilliance, the most brilliant sources are, of course, the undulators. And you can ask yourself if there are fundamental limits to the storage ring. Well, there are fundamental limits in the sense that if you assume that you have a perfect accelerator with vanishing electron emittance, these are the maximum, you take all the best undulators in the existing facilities, and then you assume that the electrons are ideally steered and focused on the ring, and you can hardly exceed this quantity. I guess I cannot move the slides anymore somehow. Let me see. I have to go back to the other view and then. Okay. No. Okay. Let me try to restart the whole talk. Okay. Sorry about that. Okay. So, okay, you keep seeing. Okay, now you keep seeing the whole picture.
Okay, we are still seeing transparency number 13.
Yes, I know, but I'm trying to do something about it. I don't know why, because we tried. Okay, so I don't know how to get rid of this picture because I would like you to see this one.
Close the window. Oh.
Well, I did close the window, but it doesn't care. This window is fixed there. Oh, okay. So we have it
Okay.
lasted. Okay. So we went to this slide now, but let's see if it moves. No. Okay. And no, but this one doesn't move anymore. No, I have to probably stop the sharing and restart it.
Yeah.
Let me see if that will. I'm sorry about this because we
No
even
problem.
a test and present. Stop sharing. Okay.
Yeah.
All right. Now I stop sharing. Now I start sharing.
Restart the sharing.
Share screen. Share screen. Allow whatever you want me to allow. Okay. Okay. Allow. And there we go. Okay.
Yeah.
So,
Okay.
anyway, what I wanted to say is that there was a revolution that was started a few years ago by the gentleman on the top of this slide, which is Mikael Eriksson from Max 2, which he made essentially a modification of how to combine the magnetic lattice and essentially to split a bending magnet in several portions, initially 2, and to make the so-called double band achromat, so that when the electron beam starts to broaden up because of the intense emission of light, it gets in the middle, it gets refocused and then goes to the second half. And then this was adopted by several people, and in particular, Pantaleo Raimondi at the ESRF extended this to the so-called multiple band achromats. He eventually managed to split the bending magnet in 6 portions and obtained fantastic results. Let's see if we can move the same problem. I don't seem to be able to move the slides. Okay, I have to do it this way. I'm sorry. Okay, so you see that we saw in the previous slides that the theoretical limit is of the order of 10 to the 22 units of brilliance, and now he is getting very, very, very close, and he's already thinking about ways in which you could do the final step and go to this green light with the so-called mini beta lattice. And another factor that drives the increase of brilliance is that you can make essentially go to machines with a very big, with a very long lattice, so that you have a place to split a lot of magnets. And so very long rings like Petra 4 in Hamburg or PEP are going to be, there are plans to do an even further step in this direction, so that there is still some future to come up. But the results that you obtain with the machines like the EBS in Grenoble are fantastic. And in fact, all the synchrotron radiation sources in the world are now upgrading to this kind of lattice, or have plans to do that, including, of course, the machine in Trieste, Elettra. Okay, now there is synchrotrons are wonderful, but they have a limitation in that it's very difficult to have an intense synchronous radiation source which has pulses which are much shorter than 10 picoseconds or that order of magnitude. The reason being that even if you manage to make a very compact electron bunch that would radiate for a very short time, after a few thousand turns, which means a millisecond, it would broaden again because of the internal dynamics of the machine and of the process of emission. So you have to think about something else, namely a single pass machine in which the electrons radiate only once. And this was a concept that was developed independently in the Soviet Union by Kondratienko and Saldin, and in the United States by 3 Italians working in the United States at the time, which were Rodolfo Bonifacio, Claudio Pellegrini, and Lorenzo Narducci. And their idea was to exploit an instability of the emission process for a very brilliant electron beam in a very long undulator, what happens is that the radiation that is going a little bit faster than the electrons begin to catch up with the electron and to order them, to give them some degree of coherence at the wavelength of the radiation. Now, when you have this sort of a bunching of the charge on the scale of the wavelength, the electrons with the same in the same bunch of the order of the wavelength dimension start radiating coherently, and therefore you get an increase of the radiation, which is spectacular. And in order to do that, you need a very good accelerator and a very long undulator. Okay, this thing doesn't work, but we have found a way around. Okay. So the promise of free electron lasers is, of course, to produce unprecedented peak brilliance, which is delivered within 10 to 100 femtoseconds duration, because now the length of the pulse is under your control, with the number of photons that you normally in a synchron you get in 1 second. And in fact, this concept for the shorter wavelengths was first demonstrated at Flash in Hamburg, then at LCLS and other places, and now there are a lot of free electron lasers around the world. And now, you know, they have, however, a problem, and the problem is that this is a process which starts from the amplification of noise. You know, you have by noise a certain Fourier component in the electron distribution inside the bunch, shot noise, say, and so the pulses are highly reproducible and they have several spikes, so it's very, very far from what you would call a laser. I should add very quickly that, of course, there are ways around this, especially for the longer wavelength, which have to do with the process of seeding, that is to say, of letting an external laser drive the beginning of the process instead of the noise. But I think Fulvio Parmigiani, if I'm not wrong, is going to talk about it, so I don't need to do that here. So there are lots of free electron lasers now around the world. Here are some examples from Italy, Japan, LCLS in the United States, the Swiss FEL in Switzerland, and this is the European free electron laser near Hamburg, which is altogether a 3.4 kilometer facility with an accelerator which is about 2 kilometers long that can reach 17.5 GeV energy. And this is, of course, realized with this colossal superconducting RF accelerator. And it has produced very interesting results, like all the free electron lasers. For instance, you can do pump and probe experiments in which with a synchronized laser, you pump the system in an excited state, and then you look at the evolution. For instance, you know, you can do, this experiment was done at the European XFEL. You shine a laser on a sample, particularly this was strontium titanate. If you excite electrons out of the bonding orbitals into the, it is as though you were weakening or cutting some of the springs that put together the lattice. And so the lattice start to have a coherent oscillation. You create optical phonons, which then can decay into acoustic phonons and so on and so forth. And they were able, as a function of time distance after the laser pulse, to investigate by Bragg reflectivity at you know, symmetric conditions, the phonons which are generated in the system. And so they could see at different wave vectors, you know, basically the diffraction on the excited phonons, and see how for a particular momentum transfer they decay. So you measure essentially the lifetime of the photon as a function of wave vector, which is and how it goes down in time on a time scale of much less than a picosecond. However, again, you think, okay, one could be happy with this, and but you know, there are some problems. First of all, we mentioned the fact that FEL radiation is not very reproducible unless you have a longer wavelength seeded, or you do some special things which are, however, quite tricky. That's one problem. And the second problem is that free electron lasers are very expensive, because if you need to make a very large accelerator, it is a very expensive proposition, as we know. So there are two activities which are going to counteract this. The first one is to try to improve the longitudinal coherence by doing what people have been doing with lasers in the optical field, that is to introduce the notion of a cavity. And this was an old idea that was originated in Brookhaven by Liu Yu, and then later by Kwang-jae Kim at Argonne National Laboratory. And they say, well, you can use Bragg optics to have, a pulse of photons partly reflected and going back. And when he enters about to enter the undulator again, there's another electron bunch coming. And so they build up, on this existing photon pulse, and then another, and then another, and then another. And this one turns out to have a monochromaticity of the order of 10 to the minus 7. But with the disadvantage, nothing comes for free, that this thing operates at only one single wavelength, because you have all these Bragg crystals that, if you want to change the wavelength, you have to rearrange the whole thing. Okay, so this one we can skip. And then there is another problem, and that is the problem that, as one American colleague famously said, that the first thing about free electron lasers is that they are not free. Because to build a very large accelerator carries a price tag of several hundreds of millions of euros. So people are trying to think about alternative accelerator principle. In a very schematic way, the principle of a radio frequency accelerator is that you send an electron bunch through a series of charged rings or accelerating cavities, and when the electron has gone through this and is being repelled by it, the next one changes and becomes attractive and pushes the electron, and so on and so forth. And you can do this at the frequency, radio frequency up to gigahertz. But no matter what you do, the limit of this can be accelerations of the order of 100 megavolt per meter. So, for instance, the European XFEL LINAC considered a great success to have cavities which had a limit of 40 megawatts per meter. It was already an excellent accelerator. But now there is the idea of using, again, lasers and concepts of plasma physics, picking up an old idea by Tajima and Dawson from the 1970s, in which what you do, you send a very intense laser pulse, which ionizes a medium, for instance, a gas, and then it ionizes the system, so it kicks out all the electrons and leaves behind the heavier and positively charged ions. If you send an electron beam inside, it will feel the attraction of the place where the electrons have been depleted and be accelerated. And the electrons will start to fall back on the back of this wave, so-called wake field, and therefore they will push from behind. And so the electrons will also be accelerated enormously. And it turns out that there the theoretical limit is not 100 megavolt per meter, but it's a 100 gigavolt per meters. So GeV per meter. So with a so-called tabletop, it's a big table because you have a big laser and so on and so forth. But in a tabletop installation, you can obtain energies of the order of GeVs. Now, this is still still needing a lot of optimization, because if you look at the different Laboratoire d'Optique Appliquée, Lawrence Berkeley, DAISY, and the Chinese facility, they have energy spreads of the electrons and emittances which are not yet very good and not comparable to what you can do with the RF accelerators. So it will take a few years of development, but certainly there is some promise because they have been observing in Shanghai a free electron lasing at 27 nanometers based on a laser wake field accelerator. This was published in Nature in 2021. And of course, if you compare, say, the Fermi free electron laser in Trieste, which operates at this kind of wavelength, well, the intensity of the wake field accelerator produces a beam which is about 3 orders of magnitude weaker, has a very small repetition rate because it's the repetition rate of these very high power lasers, but it's a very good start. You see that indeed the distribution of the energy between the shots is very broad, and so it's very unstable and very erratic. But it's just a proof of principle, and it will take probably some 10 years of development, but this is a very promising way to go. And this is a picture of the installation. You see, these are people. So as I said, it's a very big table, plus you have to have a big laser with its power supply even bigger here. So, but this is certainly a way to reduce drastically the price of these facilities. Conclusion. So the accelerator-based light sources, as I tried to show you, despite the technical problems I had, have a long history of success in powering progress in all disciplines of the natural sciences. But the story is far from over, and revolutionary new ideas are being developed and implemented, and some at least may in future take the center stage. So that's the end of my presentation. Thank you very much for your attention, and sorry again for the technical mishaps.
And for this excursus through the evolution of the radiation, the particle-induced accelerator for radiation. And okay, looking for question. In the meantime, just a question about the Wakefield accelerator. You said that you will need a few years to get to the point that we can be used for producing a free electron laser. But already inside the bubble, the electron will oscillate and they will produce some radiation. So this radiation.
Yeah, they produce radiation, but they produce radiation anyway. You know, you have so many accelerated charges, you have a lot of radiation. But if you know, it's not very coherent, it's not very stable, it's not very reproducible, and it's not very intense. So you need to, you need to tune the machine and to tune the process so that you bring all of these parameters under control. And this is something that takes a long time.
Okay.
You know, it's a little bit, it's not a new story. You know, when Guglielmo Marconi started to investigate radio, the maximum distance of transmission was 800 meters, I believe. And then after many years of work, he started to send the stuff to the United States from Europe. And so this is the same process. You know, you have to fix all the things, and very big labs are going full speed at this, but still it will take some years.
Yeah, this should be what is called this Eupraxia project that involve Hamburg, Frascati.
Yes.
Okay.
Yes. You have a version in which you send first a laser beam inside and then an electron, or other things in which you send a particle beam and then another bunch of electrons behind. So there are versions. I mean, I didn't have time to go into many details, but the principle is to go from hundreds of millions of euros to a few millions of euros. It's not something you will have in every kitchen, but still it will decrease the price by order of magnitudes.
Yes, of course. Okay, thank you very much, Massimo. And let's move to the next speaker. That will be Fulvio Parmigiani. Is Fulvio there? Yes. Okay.
Yeah.
Okay. Hi, Fulvio.
Hi.
Fulvio has been before the coordinator and then the head of the scientific program at the Free Electron Laser in Trieste. And now he's at Emeritus Professor at the University of Trieste and Fellow of the American Society and of Electrosynchrotron. He's an expert of different things like non-equilibrium physics, spectroscopy of strong correlated systems, and magnetic materials and novel emerging material. Today, he will talk about quantum light and laser-seeded free electron laser. Please, Fulvio.
Thank you. Can you hear me?
Yes.
Okay.
Yeah.
Thanks a lot for the invitation to this nice symposium. Yes, today I'm going to talk about some ideas that we have about the possibility of generating quantum light with free electron lasers. Let me make clear from the very beginning that quantum light is something very special because it's a state of the light that doesn't have an equivalent in the classical light. This work has been done in collaboration with Fabio Benatti, that is a colleague, a theorist, a quantum optics theorist at the University of Trieste, and Giovanni Perosa, that just finished his PhD in Trieste and is moving to the Uppsala University. So let me start first to try to understand in an easy way what is a laser. Well, a laser, of course, is overall a quantum device. It's a quantum device because it requires a system to be pumped in an excited state, and then the decay from this state that eventually is stimulated by the light, but to have a gain, you need the population inversion. That means that here the state 2 should have a population inversion more state than the state 1. So you have stimulated emission and population inversion. That's not enough to make a laser because you need a quantum cavity, actually a resonant quantum cavity. And it is the fact that you have a resonant quantum cavity that the emission, the stimulated emission, has a phase that is correlated to the position of the stimulated emission. And at this point, you can take some of the electromagnetic generation, electromagnetic energy that is in the cavity out from a mirror that is a partially reflecting mirror. This kind of light has a characteristic, as we will see soon, that can be measured through a photon statistics. Now, what is a free electron laser? Massimo Altarelli already said some basic principle of the free electron laser, but let me recall this principle. To have a free electron laser, you need a linear accelerator, and you need a long ondulator. So the electron bunch can ondulate and it can generate micro bunches, and these are due to the interaction of the electron bunch with the spontaneous emission of the radiation, and in simple words, what's happening is that as you increase the length of the ondulator, the electrons that are faster, they are slowed down, and the electrons that are slower, they are speeded up. And so in the phase space, essentially, you condense the charge in point of the space phase, and these charges are then oscillating in phase, and they are generating what are the spikes, the typical spikes that you can observe in a free electron laser. As already said, this is not a coherent radiation because it's a radiation that is starting essentially from the background radiation noise. And the reason why this was called laser, I believe, is because of the very, very high brightness of the radiation that you can generate in such a way. But that is, I think, the only characteristic, beside probably the transversal coherence, that a free electron laser has in common with a real laser. Now the point is the following, that if we want to make a laser in the X-rays, you cannot use anymore an optical cavity, because of course there are no optical cavities that can work in the X-rays. That is the basic issue, and I remember that I started to work on this question when I was a young scientist at the CISA laboratory in Milan with Tito Recchi. At that time, we didn't have any idea how to make, of course, a free electron laser, and how overall to make a laser operating in the X-ray domains. But to understand better this question, we need, first of all, to define some basic concepts. So what is classical coherence? Well, when we define the coherence, classical coherence is essentially an ideal property of waves in general, in our case, electromagnetic waves, that enables stationarity in constant in space and time of the property of the electromagnetic wave in our case. That means that essentially, if you look at the longitudinal coherence, that is related to the time that the electromagnetic wave travel without any interruption of the phase. So a monochromatic wave essentially is a sinusoidal wave that has an infinite phase continuity. The transversal coherence instead is something that is related to the size of the surface of the source, and essentially is related to the constant phase in a transversal plane of the propagating wave. So there are two very different concepts here that has to be considered, because longitudinal coherence is more related to the mechanism that is producing the radiation. Instead, transversal coherence is related to the size of the surface. This is basically the classical statement about coherence. How can we measure the coherence? Well, to measure the first order coherence, what we call the first order coherence, this is defined as a first order correlation between two beams that are overlapping, and eventually is normalized to the intensity of this beam. And this can be measured, for example, through an interferometer. There are many different types of interferometer. Here we are talking about the Young interferometer, which is probably the first interferometer, where the light that is emitted by source is passing through two holes here, and you can see the interference on this screen that is set at a certain distance from the two holes. And what you measure is essentially the visibility of the fringes here, and they are related to the first order coherence. So the first order coherence is essentially a measure of the phase coherence. And we call this also first order coherence. There are other ways to measure the coherence, and that is achieved, and this is the second order correlation function, and that is given by this correlation. So the intensity that is measured in a position of the beam on a screen, and the intensity that is measured on a different position on the screen, and is also normalized. And this gives is the base of an interferometer that is ABT interferometer. These are the initial of the Henry Brown twist interferometer. And essentially the scheme is the following. You have the source, you split the light coming from the source, and you use two detectors, and they are intensity detector typically, and you measure the correlation between the light that is detected on detector 1 and detector 2 that are, for example, placed at different distances just to make the intensity correlation. Well, this is a very interesting setup because it can be used in the classical regime, meaning that you measure just the intensity, but it can be used also in the quantum regime because you can detect the photon. So you do essentially a photon counting. And this is bringing me to the interesting point where you may ask, but what about higher order of coherence? Well, this was a question that has been addressed by Glauber, and is also bringing me to the definition of what is a quantum light. So at this point, of course, the electromagnetic field has to be quantized. So we have a quantum of energy of the electromagnetic field that today we call photon, and they can be measured as particles. And of course, if you detect particles, you can always look at the statistic of these particles. And in fact, this is what was done from after the quantization of the electromagnetic field and the quantum statistic of this particle. The work of Glauber, however, was to redefine in more precise terms the definition of a coherent source. So essentially, a coherent source or a fully coherent source should be coherent at any degree. So it should be first order, second order, or any order of coherence. And this is a very important step that is bringing us to the definition of quantum state of the light. As I said, this state, they don't have an equivalent in classical physics. And just to give some example, they are, for example, the entangled state, the squeeze state, the anti-bunching states. Before, of course, getting to this very special state of the light, we need to understand a previous step about the statistic of this light. And this was done for the first time by Arecki, and he and his co-worker, they measured the statistical distribution of a Gaussian laser source. And it was clear that these statistics became very different and was a Poissonian statistic when measuring the laser source, and it became instead a sub-Poissonian statistic when measuring the thermal light. So this was a very fundamental step that was done at that time. So essentially now we need to treat the light as particle and to measure the statistic of this light. Now let me go back to the question of the free electron laser. As I said, to make a laser in the X-rays, essentially what you would need in principle is a resonant cavity. That cannot be done. How can we, however, try to have a quantum light with a free electron laser? Well, the idea was to seed the electron bunch with a seeding laser. The field of the seeding laser has to be several order of magnitude larger than the spontaneous emission of the electron bunch. And in this case, what's happened is, although there is not a real consistent theoretical description of this interaction, but what's happened is that essentially the character of the laser light, for example, the fact that you are using a Poissonian light, has to be transferred to the electron bunch, and after the radiator, this character is transferred again to the photon bunch that is generated, and that would be, of course, an higher order respect to the seeding light, meaning that, for example, if the seeding light is at 100 nanometers, you may have out of here even 2 nanometers, right? This is something that has been already demonstrated, as I will show soon. But the question is, what about if here I am using a quantum light? That means, for example, a squeezed laser light. Would I obtain here a squeezed FEL light? This is a question that still needs to be addressed. But why are we paying so much attention to the coherence of the FEL light? Well, we know, as we said before, that in the Salve mode you will have many spikes, and probably these spikes are incoherent one respect to the other. So the overall bunch of this light is not coherent. Instead, if you are seeding the electron bunch with a laser pulse, you will have a quite single pulse, which is, of course, very, very close to what you expect from a real laser. But of course, having a pulse that is narrow in bandwidth, that doesn't mean that is a Poissonian light. About the transversal coherence, of course, you can measure the transversal coherence in many different facilities. And as you can see here, for example, at CLS, at FLASH, SACLA, and of course also at Fermi, you may have some advantages about the transversal coherence, but in this case, the advantages are not, I will say, so interesting as the advantage that instead you will have with the longitudinal coherence. Well, the longitudinal coherence was measured first in different facilities at Flash, Palexfeld, and also at Fermi. But remember that the measure of the longitudinal coherence at the first order is something that is really related to what we'll call the classical coherence. So it's a phase coherence. And of course, because Fermi is producing pulses that have a very high monochromaticity in terms that is a narrow band, the coherence at the first order is extremely good with respect to the Sarzi process. But the real question is, what about the second order coherence? Well, that was a very interesting experiment. That was done on a beam line at Fermi using Embury-Brown and twist interferometer. That is a variation of the Embury-Brown twist interferometer, I will say. And of course, Fermi can be used in a Sarzi mode as well as in the seated mode. And well, this measurement has been done using this optical scheme, where you can measure simultaneously the dispersion of the light, the spectrum of the light, if you like, and you can measure on a CCD detector instead the light that is spread on a significantly large detector, and you can measure the correlation between different points of this detector. That was, in my opinion, a quite interesting and smart experiment. Well, what you can see is that actually when the Fermi FEL is seated, you have a very high degree of correlation, and actually what is turning out respect to the correlation that you can see when it's in the Sarzi mode, the correlation function is equal to 1. That means that the light that is generated here with the seated FEL is a Poissonian light. So in this respect, we can say that this light is very similar to a laser light, but this is not yet a quantum light. To be a quantum light, as I said, we need to do something else, because it has to be coherent at any degree of coherence. Nonetheless, of course, having this light, if, for example, making use of the transversal coherence, you can, for example, produce the diffraction of an object, and with the phase retrieval, you can reconstruct the image. Well, this was an experiment done by Eric Chapman in 2006, and many progresses has been done in this respect. But still, I think that the main outcome that is expected from this kind of experiment, where the final target is to have the lateral resolution that is close to the lateral resolution that you can have in the hard disk rays, of course, that you can have with transmission electron microscope is still something that is to come. Another interesting feature is that the experiment that you can obtain using the transversal coherence, if you can generate light that is circularly polarized, of course, you can distinguish, for example, as in this case, the magnetic domains. And actually, in this experiment has been also looked at the pump probe technique has been looked at the dynamics of the magnetic domain. And that, of course, is a rather interesting achievement that combine the transversal coherence with a very short pulse, the tunable light, because in this case has been tuned on the copper 3P edge. And of course, in the pump probe configuration, you can look at the dynamics. But probably the more advanced experiment that has been done with Fermi was made possible because of the coherent control. And this time we are talking about the longitudinal coherence, not the transversal coherence, where Kevin Prince and co-workers, they've been able to look at the asymmetry versus the relative phase in an experiment in gas phase, and they were able also to follow in time the shape of the orbitals in a gas. So transversal coherence and longitudinal coherence. Now, the point is, as I said, that Glauber's criterion for the full coherence requires the correlation function of any order rather than one. And this criterion is satisfied by the Glauber coherence states, where these states are essentially complex numbers. So as I said, if we have a light that is has a degree of coherence of 1, it will have a Poissonian distribution. If I have instead a quantum light, so again, for example, a squeeze state of the light, I will obtain a light that is eventually super Poissonian. So it is narrow. And also this is detected through the photon detection. So essentially, what you can do in the experiment is to measure the correlation function, and you look at the possible deviation of the ideal distribution function that can be sub-Poissonian or super Poissonian or just a Poissonian line. And this is something that we would like to use to characterize the possible quantum light in the seeded FEL. But we have to define a strategy for this for this measurement, meaning that if I see the FEL with a squeeze state, I'm wondering if the FEL light at higher harmonic than the seeding is still in the squeeze state. And the point here is that, of course, you have to deal with a quite bright light source, and to measure, in this case, the photon statistic is not easy because you have to work with a large number of photons. And the direct photon counting, maybe counting photon by photon, may not really work. So we designed this strategy that actually has been used also for tabletop laser. What you can do, of course, is if you have the laser light that is coming, you can use a neutral filter, and you can reduce, of course, this light. But you can also consider the case of, instead of measuring the photon statistic, what you can measure is the off-click statistic. So no light is registered. The off-click probability, it depends on the photon distribution. The more photon, the less likely the detector will not click. For a percent efficiency, this is equal 1, off-click are not possible. Reducing the efficiency, we can retrieve the statistic of the off-click. And you need more neutral filters here, and to do the statistic at different intensity of the light. What we did essentially was just a simulation, and the statistic that we have simulated using the FEL, it seems to be very well fitting the theoretical distribution. And now I'm coming to the last point of my presentation here, my talk, of course, is the detector. We need a detector of very, very low noise, very high quality, needs a fast response, a small dead time, and of course, a high quantum efficiency. This detector probably already exists, and we are now on the process of testing this detector. There are also something advantages of using, for example, the CMOS sensor array. They can be operated in the Geiger mode. They have a very fast response and short dead time, operative at all voltages, direct integration on the chips. Pixel can be arranged to match the FEL spot diameter, and selective turn off of pixel for detection efficiency. So this is the working process. So what do we expect from this? Well, these are the perspective. We want to characterize the coherence of a seeded FEL in terms of quantum state. We still have to test what would be the best strategy. In the recent discussion, we end up with the idea that probably that can also be done measuring directly the photon statistic, so avoiding this complicated model that we call the non-click statistics. What are the motivation? Well, we will, of course, collect complementary information about the coherence with respect to the correlation function. And we hope to be able to discriminate non-classical feature of the FEL light. That meaning that the seeding of the FEL is not just a way to generate a narrowband pulse, but if I manipulate the seeding light in terms of, for example, of creating anti-bunching or creating a squeeze state, to see if this characteristic can be transferred to the FEL light. Of course, the simulation that we had done so far seems to work for a large number of photons. With large number of photons, I mean we had simulated up to 1,000 photon per pulse. Of course, they can be reached by neutral filter, and this we will also avoid the photon counting in the X-rays that as a low efficiency. Well, if that will be possible, again, we will finally have a source that is operating in the EUV and very soft X-rays with the full characteristic of a laser source. Thank you for your attention.
Thanks, Fulvio, for your interesting talk about the characterization in terms of quantum light of a radiation source. I don't see any question. Okay, just I have a curiosity. When we have learned how to manipulate the source of the field in order to have the different statistics and so know better about the coherence, do you see some specific application that we gain by using sub-Poissonian or something like that?
Oh yeah, of course. These applications are, thank you for this question. These applications are essentially related to the fact that if you have quantum state, for example, in the matter, okay, you want to test these quantum states with light. And to test this quantum state with light, of course, you need a light that is from the quantum point of view under control. This is what is done with tabletop laser, right? Well, the interesting point here is, can we extend this type of spectroscopy to the X-ray domain?
Yeah. Okay. So this is the question, right?
As the experiment that has been done by Kevin, right?
That exactly. To understand, to go to different quantum parts. If you can manage to go to different quantum parts for initial and final state and see the effect. Okay. In the meantime, we got a question: is that if you have some idea about Massimo introduced the new wake field accelerator. So do you think that at the end of the day they will be worse or better than FEL in terms of coherence? All this would be a tremendous...
The wake field accelerator?
Yeah.
Well, first of all, we need to have a wake field accelerator. I worked for several months at Berkeley with Windeman, and my impression is that the proof of principle is still to come. Of course, there is nothing wrong from the point of view of the physics. But of course, again, if you have a wake field accelerator, then typically what I expect is if I have a Poissonian laser light, is to have a Poissonian light coming out of that. But there is something in the middle that is a big question mark. That is the interaction between the laser light and exactly and the plasma. So and this it will very likely produce highly decoherence.
Yeah, I think so. Yeah. Okay. Okay. Thank you very much, Fulvio.
Welcome.
Now let's move to, let's say, play home in the sense that we are now giving the stage to colleague from the Institute of Structure and Matter, and they will introduce how we work in the field, starting with the femtolab in the Potenza section of the Institute. Please, Antonio.
Hi, good morning to everyone. I don't know if you can see my slides, if they're on.
Now, yes. Yes, they are.
Okay. So as you know, we are from Potenza. Actually, our lab is located in Tito Scalo, in the south of Italy. Although we are in the south of Italy, we have snow, and actually, even though we have so much snow, sometimes we can get this because of the need of finding solution to problems. This is something that is related to laser as well. So we know that Taunis Basov Prokhorov got the Nobel Prize in Physics in 1964 for fundamental work in field and quantum electronics, thanks to the construction of oscillators amplifier based on Maser laser principle. But actually, in 16 May of 1960, so 63 years ago, Mayman invented invented the first solid laser, so the ruby laser that and it is famous his statement, a solution looking for a problem. So our work is based on the use of lasers, and we use laser for different applications. So laser ablation liquid, laser-induced breakdown spectroscopy, pulse laser deposition, and laser-induced periodic surface structures.
Antonio, please, your slides are not moving. You are still in the first one, and you are not in a presentation mode.
Okay, I'm really in the. Can you see it?
We see the slide, but we see the first one. You got to go in the presentation mode from the PowerPoint. Okay, now you have the second, but it's still not in the presentation mode.
I'm in the presentation mode, but I will find a way. Let's.
Probably you are sharing another monitor if you have to monitor.
Okay. I'll try in this other way. Let's have a look if it works. Okay. Can you see it?
Now it's okay.
Now it's okay. Does it work? Okay. So as I said, in the south of Italy, we have snow sometime, and we find the solution so you can get the list because of mean that can remove the snow, of course. But as I said, we work with lasers, so our problem is the other way around. So we look for problems rather than solution, because the laser for us is the solution, as said Mayman in 1960, so 3 years ago. Actually, the laser and the principle are based on the discovered by Taunis Basov Prokhorov that awarded the Nobel Prize in 1964. The systems that we use for our work, research work, are, of course, a different way of using the light, amplified and by stimulated emission, so lasers, laser-induced breakdown spectroscopy, laser ablation liquid, or pulse laser deposition, and laser-induced periodic surface structures. So there is a movie showing our place where we are located. This is just a short movie or ablation liquid, so the cavitation bubble, how it evolves in time, and even the way of getting some treatments of diamonds in order to improve the absorption of this compound for solar devices, I mean, for concentrated solar devices. And so, as Mayman said, we look for problems. So our main objective is to use the laser matter interaction in different processes, and for getting different pieces of information of the process induced by laser, and even for getting new materials or devices. The laser ablation process is based on the interaction of the laser with material and the formation of a plasma plume, which by using femtosecond sources actually is formed by two components. One, ionic atomic species, which are much faster than the second part, which is made of nanoparticles. All emission of the plasma induced by laser can be even used for analytical detection of the excited species, and so we use this kind of feature for laser-induced breakdown spectroscopy, so for characterizing materials. Looking at the interaction of short laser pulses with matter, we get nanoparticles, as I said, and it can actually represent roughly 80% of the matter removed from the sample. And one of the mechanisms that can let us understand which is the process induced is the photomechanical effect. So we have a large amount of material that is ejected in form of nanoparticles. And the emission that we can get is from the ionic or neutral species, electronically excited, but even for longer times by hot nanoparticles, which can give a black body emission, which gives us the value of the temperature involved, which is roughly in this case, 3000 Kelvin. So it means that we can have a different evaporation of species involved, and at high temperatures, we can have a sort of fractionation of the composition. But actually, the radiative cooling, radiative vaporization cooling can be so combined that the deposited nanoparticles do not change actually for very high temperature, even though the difference in terms of vapor tension is of 1 to order of magnitude. So we can retain the composition of the starting target, even though we get nanoparticles, which are hot nanoparticles that are deposited and that can evaporate differentially in some cases, but actually doesn't happen for high temperatures involved. The difference between femtosecond and nanosecond is that we can retain the properties of the starting target, and in these circumstances, we can have materials for different applications, for biomaterial, refractory material, battery material components. In a laser ablation liquid, there is another effect, which is the evolution of the plasma, but as well, all process involves first a shock wave and then a cavitation bubble, which is 1 or 2 order of magnitude slower than the shock wave evolution. And actually, we have a oscillation of the bubble, and you can see the move here, where the nanoparticles are formed. But when these are generated, when the cavitation bubble collapse actually, and some high temperatures and pressures are obtained, are reached. So in terms of pressures, we can reach giga Pascal, and temperature of 10,000 Kelvin. So we have high temperature, high pressures, the cavitation bubble collapses, and we have generation of nanoparticles, which can be strongly affected by the surrounding liquid composition. So this is just a sketch of what is going on in time, and the shock wave that evolves with a speed of actually 1 kilometer per second. What we do for characterizing our materials is to have a look at species by TEM, SEM, IFM, and all material science characterization that can help us in understanding what is the process involved, even the properties of our systems, and for application for different devices. In this case, we have obtained in liquid the ablation of titanium, which after a few days from nanoparticles, we have the formation of microtubes by self-assembly of them. And actually the mechanism is induced by the presence of titanium hydroxide. And as well, because of the high temperatures and high pressures involved in the process, we can even perform the colloidal formation of our nanodiamonds. About the laser-induced periodic surface structures, we obtain by femtosecond laser applied, so in impinging on surface of materials, different nanostructures which are formed by ripples, and by Fourier fast transform, we can get the spatial periodicity of our nanostructures. And in terms of properties, even the composition can help us for different application. In this case, we have seen that simulated body fluid can grow some calcium phosphate species because of the composition and periodicity of our nanostructures. The lips can be split into different regimes. Low spatial frequency lips, when the spatial frequency of our nanostructure is roughly compatible to the wavelengths of our laser, or high spatial frequency lips, when the spatial frequency of our ripples is much less than half of the wavelengths of the laser. In terms of application, we have seen that these nanostructures, these ripples, can be very useful for increasing the absorbance of some materials like diamonds, as we saw in the previous movie. We can get the nanostructures in vacuum, but even in by using a workstation, which actually provide the nanostructure by focusing the laser beam onto the sample in air, in atmospheric environment. And in this case, we have seen that the molybdenum nanostructures induced by femtosecond laser can actually vary the optical properties by enhancing the selectivity in absorbance of the light. And a part of the nanostructures, we can have even nanoparticles that can be deposited on the nanostructure. We can even improve the absorbance of the solar light, but actually, if we use these devices in working condition, let's say 1100 Kelvin for a long time in vacuum, 10 to the power minus 5 millibar, we can see that the composition still remains the same if we use low fluencies. So it means energy per square centimeter, but actually we decrease the absorption solar light, and when we increase the fluence, we retain the solar absorbance because of the presence of sub-oxide species like molybdenum for oxygen 11. And that can open new perspectives for improving the nanostructures in terms not just of the frequency of our reports, but even the composition. Some other application recently we have seen that by nanostructuring stainless steel, we can improve the anode-less lithium metal batteries performance up to 100% for a high number of working cycles. We have developed even a new way for adjusting the features of our surface treated by laser by applying two different pulses delayed one each other. And in this case, we have used the dual pulse lips by using a Michelson-like interferometer. So by changing the delay line, so the delay between one pulse and the other, we can actually change the structure, nanostructure, surface nanostructure of our samples. In this case, we see that we can have a structured surface with very short delays, and we miss that dimensional nanostructure by longer delays. It means that it's different way, of course, of the interaction between the first and the second laser beam because of the excitation that are induced by the first and interacting with the second laser incoming beam. So, for example, in diamond, we can improve the optical properties, the absorbance properties, just by varying the delays between the two laser pulses and reach even very short spatial periods, which are roughly in the range of 100 nanometers up to 80 nanometers. And recently we have applied this to other systems. So, and the last one, but we are still investigating this, let's say, high order and symmetrical appearance, like the hexagonal aspect that you can see in this picture. In conclusion, we get back to the Maiman statement. Laser is still a solution looking for a problem even after 63 years. And I would like to acknowledge all of you for your attending this talk. Of course, all team, working team, for its support, which is, at the Institute of Structural Matter of Tito, Monte Libretti, but even at University of Basilicata and University La Sapienza, Rome. Thank you for your attention again.
Okay. Thank you, Antonio, for your presentation. I think that it's maybe it's time to move to the other, so we keep on time. And the next should be the one by Alessandra Palladini about the other lab in the area of research in the Tor Vergata, that is the Eurofel Support Lab. So, please, Alessandra.
Okay, thanks, Lorenzo. Before starting my presentation, I would like to show you a short video presentation of the lab. Okay. I'm sorry, I think the audio wasn't started. So anyway, I continue with the presentation of the Eurofel Support Laboratory. The lab is a femtosecond laser laboratory of the Istituto of Struttura, di Struttura della Materia, located in one of the CNR research area of Rome. Here is a photo of the laser system and a schematic view of the wide spectral and temporal range that of radiation that are provided by the laser system, as you have already seen in the video. The amplified laser system produces pulse of 800 nanometer with a temporal width of about 35 femtosecond and an energy of 4 millijoule per pulse, which is used to perform different spectroscopic techniques. In particular, a portion of this radiation is used to seed an optical parametric amplifier, thus generating laser pulses with a large wavelength tunability that we exploit for ultra-fast, time-resolved ultra-fast spectroscopy. This spectroscopy requires initially a photoinduced process in which we excite the sample with ultraviolet or visible or near-infrared radiation, thanks to the tunability of our laser system. Then we can follow both the photoluminescence and the transient absorption of the sample following the photoexcitation. In the case of photoluminescence, we gather all the radiation emitted by the sample, and we can resolve the wavelength of the emitted radiation. We can also delay the gate pulse laser beam to temporarily resolve the photoluminescence, changing the delay between the pulse of the laser pump and the gate pump. Otherwise, we can perform transient absorption spectroscopy on the sample. In this technique, a pump and probe beam overlapping the sample with a variable time delay. The probe beam is a white light continuum, and thus we can probe different wavelength at the same time. And the spectrometer detects the variation of the transmitted probe after the sample is irradiated by the pump. So when the probes arrives on the sample after the pump has irradiated the sample, different processes can be detected. In particular, the probe can be absorbed by the excited state generated by the pump beam, or otherwise the probe can stimulate an emission from the excited state, or finally we can have a depletion of the absorption due to ground state bleaching. This experiment does provide a bidimensional map showing the spectral.
The Eurofell Support Laboratory is a femtosecond laser.
So we can follow the spectral and temporal evolution of the probe transmitted after the sample is irradiated by the pump. EFSL works as an infrastructure and is part of the Nanoscience Foundries and Fine Analysis Europe structure. Thus, we work on many different research fields. Here is an overview of all the scientific topics we have addressed in the lab since its start in 2015. Recently, we have focused on plasmonics and on the study of the advanced materials, especially for application in photocatalysis and photovoltaics. Just a few examples of the scientific issue we have dealt with. For example, noble metal nanoparticles and nanostructures, which are particularly relevant in plasmonics as they exhibit locally surface plasmon resonance, which is a collective oscillation of the conduction electron. Thanks to this localized surface plasmon resonance, an extremely intense local concentration of the electric field can be achieved when the nanostructures are irradiated with the formation of the so-called hotspot. And so the nanoparticle exhibit extremely large absorption and scattering cross-section that can be exploited for different applications. Upon excitation, the localized surface plasmon can decay non-radiatively, generating individual charge carriers, it's to say electrons and holes, typically in tens of femtoseconds. These carriers are generated in a non-thermal distribution, and these carriers are highly energetic, so they can be exploited, for example, for induce chemical reactions in molecules that are close to the surface of the plasmonic nanostructure, chemical reaction which would otherwise be energetically demanding, or for example, these highly energetic carriers can be transferred to semiconductor, to closed semiconductor for use in photovoltaics, photoelectron, or photocatalysis. Then this non-thermal distribution of carriers thermalized to a hot thermal distribution through electron-electron scattering, and this occurs generally on hundreds of femtoseconds, and then electron-phonon collision transfer energy to the lattice in some picosecond, and finally on a longer time scale, the system dissipates heat to the environment through phonon-phonon scattering on a time scale of hundreds of picoseconds to some nanosecond. Thus, the nanoparticles can be successfully exploited, for example, as energy converters of converter of radiation into heat at the nanoscale. And so, for example, increasing the irradiation fluence, we can have a reshaping of melting of the nanostructure. Here are a system we have studied called spherical nanoparticle surrounded by an organic dye molecule. In particular, it was rhodamine, and changing the experimental condition in the preparation of the sample, we can generate a different aggregate of or chains of nanoparticles in the solution. And so we can use transient absorption spectroscopy to spectrally resolve the different structure present in the solution, and we can also follow the dynamics of the different structure, temporal evolution of the excited hot carrier inside the solution according to the time scale we have shown in the previous slide. Then we can also, for example, irradiate the sample, and thus irradiate the sample with laser radiation of suitable wavelength and fluence, and thus obtain a reshape of melting of the aggregates present in the solution. Here, for example, we have different cuvettes containing a solution of the gold nanoparticles surrounded by rhodamine after the irradiation with the wavelength of different wavelength. And as you can see, they have different color because different geometries are formed after the irradiation. Another field, another research field is photovoltaics. Here is a schematic representation of a solar cell. The sun radiation hits the cell and is absorbed inside the active layer. When there is excitation of electron, the generation of two charge, positive and negative charge. These charge carriers then moves towards the opposite surface of the cell and can be extracted to generate current. In this context, perovskites materials are particularly interesting and has attracted large interest due to their properties. In particular, solar cell based on perovskite have high absorption in the visible region of the spectrum. They have high efficiency, are easy to synthesize, and have low fabrication cost. ABX3 is the general formula of these perovskites, and we can change the composition of these perovskites, obtaining a solar cell with different transparency and different absorption of the light. Here on the bottom, we have, for example, cells obtained with different composition of the perovskite, and as you can see, they have a different color and transparency. so we can tune the absorption spectral range to thus matching different regions of the solar spectrum. What we have done using different spectroscopic techniques, we can try to relate the structural and physical properties of the active materials used in the cell and the performance of the final device. Here is a schematic representation of, for example, one of the perovskite solar cell we have studied. And as you can see, different, in this case, a different crystal structure, small and large, were present in the active layer of the cell. And so with the transient absorption spectroscopy, we were able to spectrally resolve this different structure, and we can follow the dynamics of the carrier generated after the pump irradiates the sample. And in particular, we were able to see how these dynamics change with the aging of the solar cell, obtaining in particular that when we have seen that the insertion of graphene into the layer of the solar cell reduce the degradation of this crystal in the active layer with aging, preserving the stability of the cell, and thus it can be of great utility in designing stable cells. Then, for example, we have used also photoluminescence in this field, and we have measured in particular the photoluminescence on inoperando cells, so cells connected with a circuit that can be open or short. And we have used a systematic approach, considering a large number of different devices with different structure, different composition, and different performances. We have measured the photoluminescence in both open and short circuit, and we have seen that despite the fact that neither open or short circuit photoluminescence by itself can be directly correlated with the cell performance, also considering a large number of different devices. We're measuring the quenching of this photoluminescence when the cell is switched from open to short circuit. We can, the quenching of this photoluminescence can be correlated instead with the cell efficiency. So these are some examples of how transient absorption and photoluminescence can be used to study different research topics. Now I want to list all the people that are part of the CNR, of the staff of the EFSL laboratory. And thanks for your attention.
Okay, thank you very much, Alessandra, for your presentation. And seeing the inconvenience at the beginning of the talk, maybe the webmaster.
The Eurofell Support Laboratory is a femtosecond laser laboratory of ISM located in the CNR research area of Tor Vergata near Rome. It is equipped with an ultra-fast laser system that is used to perform studies on the photoexcited dynamics of a wide range of materials, such as nanostructured semiconductors, plasmonic materials, and their hybrids. The amplified laser system produces light pulses of 800 nanometers, with a temporal width of 35 femtoseconds and energy of 4 millijoules per pulse. The pulses are so short that when focused, they ionize the air, producing a visible plasma and acoustic waves. That is the 1,000 times a second buzzing sound you hear in the background. The laser light generated by an OPA is tunable from the ultraviolet all the way to the infrared and is typically used to excite the materials studied in the laboratory. Our main technique is an optical pump probe experiment in which a material is pumped with one light pulse and then probed with a second broad band pulse, that is a white light supercontinuum. Modifying the optical path of the probe, the delay between the two pulses is changed with femtosecond resolution, allowing us to gain information on the dynamics of the charges in the materials under study. Photoluminescence is another optical technique employed in the laboratory, and it uses both continuous and pulsed laser beams. In this way, the studied material is excited by a laser pulse with the aim of collecting the photoluminescence spectrum and the temporal distribution of the light emitted. In the laboratory, these and other ultra-fast optical techniques are used to study novel materials being developed for a wide range of photovoltaic, photocatalytic, and optoelectronic applications.
Okay, so thanks again, Alessandra. And now the time is, okay, we can thank all the speakers of the morning, and we'll resume the session at 2 o'clock with the afternoon talk. Okay.
Thank you.
Thank you.
Thank you.
Pronto?
Sì,
Mi
buongiorno
sente?
professore. Sì, possiamo provare.
Può togliere questa musica di fondo?
Sì. In realtà stiamo registrando già. Quindi quello che possiamo fare.
Devo vedere come fare lo sharing, come sempre si fanno le cose all'ultimo momento, poi succedono dei problemi.
Ok.
Io non riesco a fare lo sharing adesso, non so dove devo andare, mi dica
Allora,
lei.
present, c'è un tasto in basso sul banner.
Share screen.
Share screen.
Adesso vediamo. Sì, ma la stessa roba dell'altra volta, che adesso in tier screen, non lo so, in tier screen, sì, ma devo aprire la presentazione, prima cosa. Lei la vede il mio schermo?
No, ancora no. Deve cliccare sullo schermo e poi fare approve.
Ma non c'è un approve qui, io sono sul mio schermo e l'approve non lo trovo. Entire screen. Share. Facciamo cancel. Non sapevo che succedeva, io l'avevo detto dovevamo trovarci prima.
Non abbiamo ancora tempo.
Cioè io ho messo su presente adesso, ce l'ho sul mio, quando vado su presente c'è scritto share screen, giusto?
Sì.
Ecco, poi c'è scritto share screen, don't share. Share screen, va bene. Ecco, adesso choose what to share.
Sì.
Choose what to share, ma non riesco a vedere niente. Windows.
Aspetti,
ecco qua, sì. Lo vedi adesso?
Sì, adesso sì, lo aggiungo, eccolo qui. Perfetto.
Vado in presentazione.
Ottimo, sì, funziona tutto. Allora, lo può lasciare in... Tanto stiamo per iniziare, lo può lasciare adesso lo rimuovo e poi lo reinserisco appena riniziamo.
Quindi fa tutto lei?
Sì, tutto io. A dopo.
A dopo. Allora, io comunque adesso non lascio lo schermo. Siamo in collegamento sempre.
Sì, ma lo lasciamo noi, cioè lo lasci così in sharing e io lo metto, diciamo, lo
rimuovo.
rimuovo.
Solo vedere un secondo, un attimo. Hide, scusi. Come non so vedere. Un momento, scusi. Effettivamente c'è abbastanza un numero di animazioni. Ecco, direi che ci siamo. Aspetti un attimo. Adesso mi metto sulla prima pagina. Power Presentation Mode e direi siamo a posto, quindi.
Perfetto. Ok, a dopo.
Grazie.
So, good afternoon to everybody, and better, good morning for the people connected from the US. Let's start our afternoon session, and the first speaker will be Professor Federico Capasso from Harvard University. Federico Capasso has been more than 20 years at the Bell Labs in Murray Hills as a researcher, manager, then vice president of the physical research. Then he joined Harvard University, where he is now Robert Wallace Professor of Applied Physics. His main contribution or main achievement was in the field of the engineering of bond structure and quantum cascade laser. Please, Professor Capasso.
Okay, thank you very much for the introduction. I'm honored to present this talk in the International Day of Light. And so the topic is flat optics, and I'm going to cover both the high-tech type of applications, such as meta lenses, talking even about the production, to the more researchy aspects, such as structure like light and dark using metasurfaces. These are the funding agencies. And this is just, I want to discuss that the main building block is the metasurface, which is a sub-wavelength spaced array of optical elements. So you can locally control the actual phase. And if you take the envelope of the wavelengths using Huygens Fresnel principle, you can predict, you can construct rather the wavefront in principle and arbitrary distance from the metasurface. In general, you can go beyond controlling the phase. You can control, of course, also the amplitude and the polarization. So the benefit of this approach from a technology point of view, it's lithographically defined. So that means you really can make flat optics in the sense of elements that can focus light, can manipulate light, using the same technology that is used to make in integrated circuits. From a lithographic point of view, this means deep UV lithography and also beyond, like EUV and so forth. And so this is on the technology side. And this, of course, opens tons of applications and high volumes. The key point from the physics is the unprecedented control of the dispersion. You see, these elements can be considered as tiny waveguides. And by changing, for example, in these pillars, the diameter, you can control the overlap factor with the incident light. So you can control the effective refractive index locally, point by point. And this adds a design element that simply is not available even in present-day diffractive optics, such as Fresnel optics, multi-level optics, and actually so forth. The advantage is you can overcome the limitation of conventional optics in terms of the aberration and achieve multifunctionality. This is a very interesting aspect. And this is a review article that we wrote a couple of years ago, basically. So this is the big vision of flat optics. Again, I want to stress that metasurfaces provide arbitrary control of the wavefront. They enable flat optics. And the key point is the middle bullet there, the same foundries, and this is happening as we speak, that manufacture camera sensors will also manufacture lenses using the same technology. So we are talking, and this is not in 5-10 years, it's going to start happening in a year or actually 2 from now. It's happening now in fact, though I can't say much on it, to achieve CMOS compatible flat optics for high volume markets. So we are talking here cell phones, laptops, and so forth, sensor for cars and so forth. And on the second part of my talk, which is generating arbitrary vector beams using metasurfaces, well beyond the capabilities of SLM. I don't have any particular application here in mind, but often happens you start with more basic type of research and you end up ultimately doing something useful. At least that's our hope in this area. And I want to stress, although I have very little time, to the importance of inverse design in the future, whether as physicists we like it or not, it's immaterial. It will have a major impact on actual optics, and we have started to work in this area as well.
So this is an example of a few years ago with my group, proved exactly the main point I said before, that using conventional deep UV lithography used to make chips, we fabricated lenses, the simplest possible lens made of glass, where you have about 160 million nanostructure per lens. It's diffraction limited. Basically, inherently, this has no spherical aberration, as you can see here from the right, and you have a nice, well-defined diffraction limited spot with a high strail ratio. So this immediately pointed to the unification in the future of two industry, integrated circuit and optics, and in fact, it got a lot of attention also among companies. So this is the latest. We had a challenge from DARPA, who has been funding my group for 5-6 years, to make the largest possible metal lens. So my people rose to this challenge and fabricated a 10 centimeters metal lens. And again, here visually, you can see the relative advantage compared to conventional commercial refractive optics. Here is our lens. This is Edmund Optics. And you can see what's the advantage. Well, there is a reduction in thickness by almost a factor of 50. There is more than a factor of 10 of reduction in actual weight, and there are other advantages as well. So this can have some interesting application for space, for example. So my group jumped on this opportunity. This is still work that is unpublished, ready to be submitted soon, and decided to mount it on an actual telescope on the roof of a building nearby. And of course, there is a filter to get rid of the background, and they did a simple test. How can this compare to conventional optics? So they decided to look at the nebula, the North American nebula. You can see here on the left with a metal lens, and this is comparison with the conventional refractive optics. So even though this is qualitative, and I don't want to particularly make too many claims, it's certainly indicative of the advantages of flat optics for application, including the scientific ones. And now I want to talk about Metalens. It was a spin-off from my group in 2016. And what we again saw the convergence of electronics and optics, integrated circuits and flat optics. So we got a head start. And right now we have 30 people. We are beyond the startup stage. We had a round B of investment recently. And a telling sign is some of the strategic investors that support Metalens. There is Intel, there is Applied Materials, there is 3M, and so forth. And so here really to target the high volume consumer electronics and automotive market, okay? And the central idea is to be fabless. We do the design, the actual prototype, but then the big foundries are going to make this because they are already the technology platform. You see, that is the key point. So this shows the existence proof, okay? The way you do the electronics, basically you have an electronic design file, you enter it in your lithographic system, and it spits out this 12-inch wafer of silicon and so forth. In this case, instead, you have an optical design file, and this is a demonstration of a generation of a 12-inch wafer. This is of glass with 10,000 amorphous silicon meta-optics for applications such as depth sensing, face recognition, and so forth. So this is very significant. This was done, in fact, in a major semiconductor company. And so it's, in a sense, more than an existence proof. It's actually here. And I want to mention one of the advantages of doing flat optics. Take a conventional sensor here to the left. It's made up of multiple plastic lenses. You see there are different materials and different shapes, and the alignment is very critical, and it's significantly thicker than if you use flat optics. The key point here, the intensity fades away from the center. That's physics. There is no way around with refractive optics. As you move away from the center, the light travels for a longer distance, so the intensity is actually less towards the edge of the sensor. But you can make, with a very simple system like this, just an aperture and a single meta-optics, you can achieve telecentricity. Means basically in intensity that is practically uniform up to the edges. You see here two pictures of one with a full plastic conventional contact sensor here, and one with actually meta lens, and you see not only the greater uniformity, but also the higher brightness, so increase signal to noise. So in fact, in last year, Metalens and ST Microelectronics, that is a major company that makes chips and delivers consumer electronic product, went into an agreement to have optical metasurfaces for vision. This stuff is entering the system right now. Unfortunately, because there's a lot of proprietary type of information, I can't be more specific than this, but I can only say something, that within 2 years, you will see meta lenses. You will see big foundries entering in this and delivering meta lenses in actual cell phones and other systems such as laptops and so forth. I think it's an irreversible process for the reason that I tried to highlight before. Now I want to move more to the research part. You see, these are single wavelength lenses. You might say, why single wavelengths? Well, if you want to do depth sensing, face recognition, you don't need an achromatic broadband lens. You can just focus. In fact, the lenses I showed you before were designed for the wavelengths of vertical cavity surface emitting laser that I know are part of the, for example, the face recognition system in the actual iPhones. Okay, so it's a wavelengths around 900 nanometer. But so there is a high volume market just for these, what I call single wavelengths meta lenses. But of course, we are ambitious. We said, how about trying to make a broadband meta lens, much simpler than conventional one. If you try to make a broadband achromatic lens, there is no way to do it with a single refractive lens. That's just the physics. So you have to use multiple refractive lenses and different materials, so they are bulky and so forth. So in this work, we showed that with a single meta lens, essentially using dispersion engineering, we can achieve achromatic focusing across the visible, as you can see here. And in fact, by designing the dispersion, these meta optics here, we can achieve either a meta lens that acts as a refractive lens, meaning that it focuses the shorter wavelengths at shorter distances, or as a diffractive lens, as you see here on the right, which does tighter focusing, shorter focusing length at longer wavelengths, or in this case, an achromatic lens. So you can literally engineer the behavior of the focal lens with frequency using this type of diffractive optics, using meta optics. You can even do white light focusing and so forth. The limitation of this strategy so far is the difficulty to make these lenses really large, so we managed to do this only for 100 micron. We should be able to overcome this, but we are not quite there yet. So we decide, let's take a step back. Why don't we make an RGB lens, a meta lens that focuses the primary colors, red, blue, and green, for applications such as virtual reality. So for that, we decide to do inverse design, because you have to make lenses that are realistic diameters, like 1 centimeter. So inverse design is sort of simple conceptually. What you determine an objective function. For example, maximize the intensity of light at a certain distance. You start from a random design, and then you do a series of loops where you calculate what your target is, and by readjusting these actual structure here, so a series of loops, you can converge arbitrarily close to what your objective function is. And this is called inverse design. In particular, this is called a joint optimization method. This was done in collaboration with a group of Steve Johnson at MIT And these are the results summarized here, 1 centimeter. This is titanium dioxide, like the previous one. For the visible, we use transparent titanium dioxide. And you see we're able to achieve essentially the same focal lengths with only changes of 0.03% of the design wavelengths as we move from the blue to the green to the actual red. So we started to play a bit. We made a VR setup, and we showed we could make binary virtual reality images with well-resolved pixel, grayscale via images and color mixing, and also did a nice movie. Okay, so now what I want to move is to the latest thing. This work that we published in Science with a group of Martin Schulz. And the idea is, we said, can we make an extreme UV metal lens? You know, extreme UV is the frontier of technology, but it's also a frontier of science. And this deals with this famous field of attosecond, of achieving attosecond pulses with high harmonic generation. So high harmonic generation, this is a system that we used. Our collaborators in University of Graz use an IR driving laser. And this is a well-known, but I want to quickly summarize. So you focus this in an argon-filled tube, and you generate a series of, you generate 1 attosecond pulse every half cycle of the driving laser. So you can create many harmonics. Odd are harmonics of the driving frequency. So now here comes a neat idea that my postdoc, Markus Osiander, who now in fact works at University of Graz, had. It's really cool. The idea, he said, how can I focus now ultraviolet light, this extreme UV light? So I want to use a platform of silicon. And the interesting thing is that in the wavelength range around, tens of nanometers, the actual refractive index of silicon is less than that of vacuum. So it's less than actual unity. Okay, so you can use the vacuum. We call this vacuum guiding. Vacuum, we are not saying air. You cannot use air when you work with extreme UV, right? So these are lenses that are immersed in actual vacuum, okay, and they focus light by where the guiding is provided by the empty part. That's the innovative aspect. And because of this refractive index of silicon, which is negative in this wavelength range, well, what's the point? Is it worth it? So my group did simulation of a metasurface lens in the extreme UV, as opposed to what's used conventional technology. You see, there is no conventional optics for EUV. You either use mirror or you can use Fresnel zone plates. You see, when you use Fresnel zone plate, there's a lot of extra stuff you really don't want. Look here in a transverse direction, but if you use a metasurface, you can clean up the focal region significantly. So basically, what my group did is make this, and this was really a tremendous amount of work over a 2 years period, managed to make these ultra-thin membranes, holy membranes. And the driving force of this technology is Marina Mereska. She's a researcher in my group, and also Daniel Lim. And so, and then our colleagues probed this, they focused light essentially with this metal lens here. They were interested in particular the 21st harmonic of the driving field, which is lambda equal 50 nanometer. And basically now, how can you measure the focal property of this? You cannot use conventional optics. So we resorted to the traditional method of a knife edge. You move a knife edge, a razor blade, basically, both perpendicular to the focal line, to the axis, or parallel here. And by watching the intensity profile as it changes when you do this, you can actually, that's exactly done here, through these curves here, where you move laterally and up and down, you can determine the actual beam waste, and it's close to what you calculate. So this is the beginning, I think, of an exciting area of research. The last part of my talk is to talk about optical singularities of light. What is a singularity? A singularity is, it occurs when a parameter is not define. For example, North and South Pole, you cannot define the longitude. So that's a so-called coordinate singularity. We all know about gravitational singularities, and well known in optics are the so-called optical singularity due to vortex. You can create a wavefront that spirals around the propagation direction. There's a helical wavefront, and you create optical vortices where the intensity at the center is 0 and the phase is undefined. So these are on-axis line singularity on a straight line. So we've asked the most general question: can we create two-dimensional singularity, sheets of dark where the phase is undefined, or zero-dimensional singularity, sort of dark spots? Okay, so this is how we formulated in general the question of phase singularity. It's about structuring dark, right? Of course, you can describe the electromagnetic field as a sum of a real part and an imaginary part. Is a complex field. You have amplitude and phase. And the intersection of the real and imaginary part, you set it, which is equal to 0, and gives the singularity. And this singular region can be either a spot, can be a line, circular line, a straight line, as I said before, or a sheet. So we focus on the question, can we create a dark sheet of light? That's a very interesting physically. It might even have some application, to study defects in materials and so forth. I think quite exciting possibility, stress tomography and so forth. So the technique, there's a lot of simulation here, and I will slip it literally under the rug because of time. But the recipe to create the sheet singularity is you specify what is your desired sheet, okay, the target sheet, and then you want to maximize the phase gradient orthogonal to the design sheet. And this was published recently, a year ago, in Nature Communication. And so my student decided, let's make a heart shape singularity, singular region. This is a singular surface. And once we create it, how are we going to look at? Well, we have to create an optical system so that we can translate along the propagation direction and see if we achieve. In fact, I'll show you the full metasurface here. This was used titanium dioxide at visible wavelengths. And you can see here that this is a particular cross-section. Indeed, we have a singular region here. Here's the phase, simulated phase, and this is the intensity. Now, of course, there is still a background, but it's unquestionable that for the parameters that we designed this, we actually do achieve the predicted heart shape, cross-section of this heart-shaped surfaces. So, in fact, this is the optical system. And as we translate this with this tube lens here, you can see there is still a lot of background. So we are not quite there yet, but we are close to really, we have to manage to suppress this actual background. But it's basically, we have already, in the sense of the shape and where it occurs, for which parameters and at what distance, we are already there. And I would say that the pioneering theoretical work on singular optics was done by Michael Berry in a very famous paper a few years ago with NIE, NYE. And the next thing we decided, why not to make dark singularities, basically spots of light. You see dark regions here that are singular, and particularly an array of equally spaced singularity. Why? We want to make a blue detuned trap. You see the famous traps, optical trap, for which Ashkin a few years ago got the Nobel Prize in physics. They are red-shifted trap. Basically, you have an atom, you have a colloid, you want to trap it in the focus of a lens, you want to redshift the laser wavelengths towards the red side, so then the particle can be shown to be attracted to the focus. And this is the famous gradient force. But it's well known that you could make a dark trap, only they are not so much developed so far, so that when you are blue shifted, the particle, the colloid, the atom, whatever, is attracted towards the dark region. So that was our goal, our vision. So for that, we use inverse design, where we dictated the objective function. So it's essentially to have creation of singular point, maximizing the actual phase gradient, and enforcing trap uniformity, right, where you see the arrows here. So that's the goal. And in fact, technology that Daniel Lim developed is really, you can see, even visually beautiful, as you can see from here. You can see this phase basically this creates the phase map necessary to achieve an array of dark traps. And again, titanium dioxide is a platform that we use routinely for the visible. This was done, in fact, for green light. And these are the experimental results. These are the numerical simulation here. Okay. Sorry, yes, we have the numerical simulation. Then we have the experiment where we take both a horizontal X cut and a horizontal Y cut. So you can see good trap uniformity. And here actually is the intensity, I mean the transverse XY cut. You can see here clearly where I'm pointing my cursor here, the singular region. So then the last topic is, how about structuring light along the propagation direction? Can we achieve a better surface so that as light propagates, the polarization changes along the axis, or the vorticity? You create optical vortices that change along the propagation direction. And can you play fancy games such as I change the incident polarization from elliptical this way to the perpendicular ellipsis? I can get a different evolution of the vortex from low to high or high to low in a somewhat arbitrary way by design, or create then something that combines this with this. I want to dispose of an objection here. First thing you can think, Federico, you are violating spin and angular momentum conservation because they cannot change in actual vacuum along the propagation direction. Correct. The statement I made is valid around the optical axis. So around the optical axis, if you do simulation, the experiment, you do see these vortices that change. You do see the polarization that changes. But you are only looking at the center. If you actually integrate the spin and the optical angular momentum density in the transverse plane, you see that as you propagate along, these are conserved quantities. So we are not violating any physical law, but can achieve the structuring of light in an angular region that is not negligible. We have gone up to, 5-10 degrees, okay, over a significant distance of up to several centimeters. Can this be useful? Maybe. Micromanipulation of color, maybe for communication. I don't know. It's just premature. So far, we're just having fun. Okay, so this is what was the first goal, to essentially, achieve a virtual analyzer. And to be useful, the beam has to be collimated. So we decided to create bezel-like beams of varying polarization along the optical axis. So for that, there is a lot of theory behind, developed in this paper, science paper called matrix Fourier optics. Is a powerful generalization of Fourier optics that involves the vector aspects of light, the polarization. So essentially, the metasurface creates a superposition of pencil-like. So these are collimated bezel beams with different cone angles and different polarization. So it creates an interference, and as the light propagates, this superposition evolves in such a way to change the polarization point by point near the axis. Okay, so again, the bezel beams are because you want to try to maintain the beam as tight as possible near the optical axis. And does this work? Yes. This really acts as a virtual analyzer. We use a 4F optical system, translated it, and you see for incident X polarization, it's as if you had a virtual polarizer along the propagation direction. This is Z. And as you move along, it's as if you are rotating, the polarizing intensity fades away for one polarization. For the perpendicular polarization, you get the opposite behavior. So it's really kind of neat. The next thing, can we do what I said before? For an incident polarization, change the optical angular momentum as it propagates near the optical axis, the light, and when we hit it with the perpendicular polarization, achieve a different behavior by design. where we change from this vortex to the other. The physics behind it sort of related to what I said before. Well, now it's a bit more complex, okay? What does the metasurface create? It essentially creates what we call optical angular momentum combs. These are combs. These are the vectorial components of light that are equally spaced in the spatial frequency domain. What is spatial frequency? Is the component of the wave vector along the propagation direction. So it creates these combs. They propagate. In propagating, they interfere, and by design in such a way that at one end it looks like a vortex with a optical angular momentum of L1, and at the other end this. So it's all a game of constructive and destructive interference, okay? And so that's the point. And so my group designed these nice metasurfaces. Here you can see they even look always visually nice, which is kind of neat. And we use this system here is a 4F system. So we reproduce here, okay, near the 4F, what's after the actual metasurface. And we can control, we can design the incident, change the incident polarization by using a half-wave plate and a quarter-wave plate. In this case, we want elliptical. And then we want to measure the spiral, right? How many arms of the spiral? This gives the optical angular momentum. So this is a known technique. We have to divert the original beam, say Gaussian beam. Okay, no, actually, yes, the Gaussian beam. Here it becomes a Bessel beam here, and interfere it with the generated beam. And the interference pattern will actually give you this spiral structure. So does it work? Yes, it works actually. I hope I can start this movie. I had problems. No, I had problems. Oh, yes. So you can see here we are stepping the camera along the Z direction near the 4F, the second focus. And you can see, we see this evolution. L plus is this polarization here, elliptical. And then this instead, when we hit it with the other polarization, you see, we actually see the opposite. We have a different behavior. And this shows the actual snapshot of what the actual movie shows. So we have a very good demonstration. So in summary, we can create structure light, structure dark with metasurface. As I said, there are potentially some very interesting applications. You see, the dark is not diffraction limited. This is one of the reasons why they gave the Nobel Prize years ago in chemistry also to actually Stefan Hell. He used this, right? So our idea here is to use this structure dark to look at, for example, defects in materials that are much smaller than the diffraction limited. For example, point defects. So maybe we can do some kind of stress tomography using structure dark. This is a bit a long-term vision, but I think it has some scientific merit to think about in this direction. And this now allows me to get to the end of my talk. And basically, I showed you, I hope, the significance and potential of flat optics based on metasurfaces. Technologically, again, the convergence of what the foundries do with semiconductor technology and the fact that you can use semiconductor technology to do optics is going to be game changers for high volume market. I'm not stating, of course, there'll always be plenty of application for refractive optics. I'm talking here of the space of consumer electronics market and so forth, and possibly, other application as well. I showed you some space application, so there are the multifunctionality. Well, I showed you some example multifunctionality. You can design flat optics to do any kind of manipulation of the waveform that you actually want. So you can generate arbitrary vector beams. And then the importance of inverse design and eventually co-design of hardware and software. So I believe that AI will have a very significant impact on optical design. This work could not have been done without some fantastic group of students, postdoc and external collaborator. I mentioned already the group of Martin Schulz, the work we have been doing with my group on EUV lenses, the group of Professor Steve Johnson at MIT, or Professor Doug Werner at Penn State University. I didn't have literally time to talk about the work with Corning, but we have done interesting work on essentially making max-Dmax metasurfaces to couple light to multi-core fiber, to few mode fiber, and so forth for spatial division multiplexing. And he is the group leader here at Corning of this effort. And I want to highlight Rob Devlin, who is the CEO of Metalens, Marina Mereska, I mentioned, J1O, who did a lot of work in various aspects, Junsu Park driving the large lens work. I mentioned Marcus in the work on EUV, Zhao Yi on the work on RGB metalenses. Arman Amirsan is a very interesting young student who works in different topics. He was instrumental in the space application of metalens. I mentioned Daniel Lim. Finally, I want to mention Christina Benea Kelmus, who spent 2 years in my group. She's a professor at EPFL, and she contributed to many aspects of the actual work, including active metasurfaces. Because of time, I couldn't cover. So again, thank you for this invitation, and I'm happy to answer questions.
Thank you very much, Professor Capasso, to introduce us to all the possibility of the future that will be reality soon of the use of the flat optics. There is a question from the web. I have only a very simple question. How thin are the XUV lenses? Can they get damaged by the beam? This was the beam.
No, they cannot be damaged by the beam, but they're very thin. You know, this is tough because you literally have to perforate a membrane. So you can imagine that the transportation, even on a plane from Boston to Vienna, was okay, but they're very fragile. It's a demonstration. It's a good question. So how to make them larger? It is a challenge. We are thinking about it. We have several ideas. Because again, any material that you put other than that can be absorbed, so there are many challenges. Damage so far, they haven't seen damage from the primary, the near IR, they haven't seen damage, let me say, but again, these are all good questions. I mean, we are at the baby stage of this research. It's just promising, and it points to an interesting direction. I don't want to make any claims of impact so far, except it is an exciting direction.
Yeah, on the same topic, so you show an example with the 50 nanometer. Do you expect that you can go slightly higher, something like 13 nanometer?
Oh, yes, for the wavelengths, yes. You need to change. We have looked at it. In fact, we added a paragraph to our science paper. You can use other material. I believe one was sort of maybe hafnium oxide, I forget, so that by doing different materials, you can cover different EUV windows. It looks possible. We haven't done it so far. We're just concentrating on, actually, that is crystalline silicon.
Okay. I don't see any other question on the web. So I think that we can thanks again, Professor Capasso, for your presentation, and then we can move to the next talk.
Thank you.
And the next one will be presented by Professor Francesca Caligari. Hi, Francesca.
Hi.
Francesca leads the Attosecond Science Division at DESI and is Professor of Physics at the University of Hamburg. And the main focus of her activity is to control in real time the electron dynamics in system of increasing complexity. Okay, so please, Francesca.
Thank you very much, Lorenzo, for the nice introduction and also for the kind invitation. It's a pleasure to present our activity after all these very nice talks and contributions today at the International Day of Light. Indeed, the title of my lecture would be Imaging Matter at the Electron Timescale, but I wanted to add light for imaging matter at the electron timescale, because the key ingredient here is really the light source we work on to be able to capture indeed these ultra-fast dynamics. So let me mention that we are located in Hamburg, as Lorenzo Valde was anticipating, and Hamburg has been It's particularly famous to be hosting a very big harbor, and therefore light sources in Hamburg have been always a big topic. And in the past, of course, this was mostly in the development of advanced lighthouses. So that was a lot of engineering for several centuries in order to aid basically the shipping to be successful in the harbor. So now there are still over 40 active lighthouses along the Elbe, which is the big river that is bringing the big ships here to Hamburg. But the most advanced light sources are no longer lighthouses, as you may imagine. And it was already nicely covered this morning by Massimo Altarelli. Indeed, we are hosting very advanced light sources that are shining nowadays in Hamburg. So we have a synchrotron, a Petra 3, and a flash, which is a BUV soft-X free electron laser hosted at DESY. But we also have the European XFEL, which is an X-ray free electron laser, a super bright X-ray laser, which is, of course, advancing the frontiers of the science we can conduct using these advanced light sources. I would not cover the science, which is investigated using the free electron lasers, as this was done already in the morning. But I would instead present tabletop light sources, which are in fact driven by conventional laser sources, and that are meant to push for extremely short pulse durations, in fact, in the attosecond time scale. And these are developed within my group at DESY. Here you can see some pictures of the laser sources and the vacuum chambers that are hosting actually our attosecond sources. So let me start by discussing about the timescales in matter, which is the key ingredients here. So as we zoom more and more into matter, as we are dealing with higher energies or higher energy scales, and this means, of course, faster and faster mechanisms. So it's well known that, for instance, structural dynamics in matter, so for instance, molecular vibrations or change in structure are happening within a time scale from the picoseconds down even to the femtosecond domain. But when we talk about electrons, then we basically move from the milli-eV energy scale up to the electron volt and even kilo electron volt scale, depending on the electronic states that are into play. And this means that we are indeed looking at faster processes from the few femtoseconds even down to the attosecond domain. If we would be able to follow even more inside matter to the nucleonic motion, then we would need even zeptosecond sources. But for today, we are limited to accessing the electronic motion, and meaning to the attosecond timescale. Just to give you an idea why it's important to follow dynamics of matter over the entire time scale, I would like to bring up a very nice example. This is actually the DNA photoreactivation mechanism. So as most of you know, when we are exposed to UV light, which is penetrating our atmosphere, we could get damage of our DNA. And in fact, this is, of course, the primary mechanism responsible for the development of skin cancer. And in fact, the damage relies in the formation of a covalent bond between two thymine nucleobases. And this is actually interrupting the nice sequence of our DNA and creating the genetic miscoding. There is, in fact, a photoreactivation mechanism which is protecting us from this damage. And again, it's activated by light, and it's operated via a photolyase enzyme, which is schematically represented here. And the photoreactivation mechanism is, in fact, based on a chain of events, starting again from the absorption of light from the HDF protein complex. And the first mechanism happening is, in fact, an ultra-fast electronic rearrangement. This intercoulombic decay is, in fact, responsible for a transfer of energy to the second part of the enzyme, which is the FADH charge donor complex. And as a result of this energy transfer, an electron is then finally transferred to the pyrimidine dimer. And in fact, this charge transfer is responsible ultimately for the breaking of this covalent bonding and therefore the restoring of the DNA sequence. This is just to transfer the information that in fact there is an ultra-fast chain of events, which is ultimately leading for a very complex photobiological process, the DNA reactivation. And it all starts with a purely electronic mechanism. So it's really important to follow all the time scales, so to say, and all the processes from the faster processes that deal with electrons, purely with the electrons, up to the structural changes that molecules undergo at later times. The way we can explore the ultra-fast time scale is to use, as it was already mentioned in the previous lectures, is the use of ultra-short light pulses. We need, in fact, light pulses which are as short as the physical mechanism we intend to follow. And the mainly used approach for performing a time result measurement is called pump and probe, where we use the first pump pulse to excite our target, our sample. So we bring the sample into some excited state. And then we probe the following dynamics or relaxation with the probe pulse, which is sent at variable delays after the pump pulse. In fact, we can detect several things. We can detect the light going through. We can detect charged particles created after the interaction with the probe pulse, and so on and so forth. And in fact, we don't care if our detectors are extremely slow, because what is dictating our time resolution is the duration of the light pulses we are using. So as we said, again, the duration of the light pulses needs to be as short as the dynamics we want to explore. So in fact, the progress in the development of laser technology or laser sources has opened the possibility to access faster and faster mechanisms. As you can see in this very nice graphical representation of the briefest events ever measured along the years, we can observe a very nice correlation with the progress in the laser technology. As you can see, there are some points in which this has been drastically improved. For instance, at this point here, there's been the discovering or the introduction of the chirp pulse amplification technique, which I don't have time to go through. This has been a Nobel Prize in physics, and it has allowed indeed to shrink very consistently the time resolution of our experiments, since the laser sources could have been brought towards shorter and shorter pulse duration and access ultimately the femtosecond domain. And therefore, it has been possible to observe in real time, for instance, the breakage of a chemical bond, or in fact, the chemistry in action. This was at some point reaching a saturation again, and until the introduction of the attosecond technology, which indeed has allowed to explore now the electronic motion in matter inside atoms at the beginning, and then molecules or more and more complex targets. So since 2000, the introduction of this attosecond technology has quite revolutionized the time result spectroscopy and given access to novel phenomena. Attosecond light pulses are not available out of conventional laser sources. In fact, laser sources can deliver femtosecond pulse durations, and this is in fact also intrinsically limited by the carrier wavelengths of these sources and various other aspects. So the only way to obtain shorter pulses is to shift the carrier wavelength from the near infrared, which is the typical carrier wavelength of for instance, the titanium sapphire laser, to the extreme ultraviolet or the vacuum ultraviolet. And this is done exploring an extremely nonlinear process, which is called ion-harmonic generation. I will dive into it in a moment. But basically, this nonlinear optical process is based on the idea of achieving very high laser intensities, in fact above 10 to the 14th of a square centimeters, that you can reach by focusing a laser pulse into a gas target, for instance an atomic target, and then to drive these nonlinear optics beyond the perturbative limit to obtain radiation at higher photon energies and with much shorter pulse durations. The process has been already mentioned in the previous presentation by Professor Capasso. I would give you a little bit more details about it. So it can be nicely described with a semi-classical model, which is actually very accessible also by non-experts. It has been introduced in 1993 by Paul Corkum. In fact, when you focus an intense laser field over, for instance, an atomic target, the amplitude of the electric field of the laser is now comparable with the electric field experienced by the electron into the Coulombic potential. The Coulombic potential is therefore deflected, it's deformed by the presence of this dressing laser field, and the electron can now tunnel out from the parent atom. This tunneling ionization is in fact the only quantum step, because everything else can be nicely described classically. In fact, now you have a free electron in the continuum, which experiences the presence of a laser field, and therefore it is accelerated. The laser field is oscillating, so the electron, which is ionized, is accelerated in the continuum far away from the atom, and then it's driven back by the laser field. And then there is a non-negligible probability of recombining with the parent ion, and via this recollision event, the excess of energy which is gained by the electron in the continuum is released as a form of a photon, which is now a high energy photon, as I mentioned before, in the extreme ultraviolet region, and it has a very short duration. The typical emission is something like this. So you have discrete peaks, and it exhibits a cutoff frequency, so it doesn't extend forever. Of course, there's a maximum photon energy that we can reach, and this depends over several parameters, including the laser intensity and the laser driving field wavelength. Why we get shorter pulses? Well, every half cycle of our infrared driving laser pulse, we have this three-step mechanism, so we can emit a very short XUV pulse. This is happening in half a cycle, as I was mentioning, but the laser field is composed by many half cycles, and therefore we end up with the train of attosecond pulses in the time domain. These attosecond pulses are separated by half of the period of the laser field, as I was mentioning, and this in the frequency domain, in fact, nicely corresponds to a comp of odd order harmonics, which are then separated by twice the frequency of the driving laser. So this is a pulse train, so it's nice, but it's not yet a single attosecond pulse. In order to achieve a single attosecond pulse, we can apply a trick. We can, in fact, play with the polarization, for instance, of our driving field, as such that we can confine the iodoharmonic generation process only to one half cycle of the driving field, and this would now correspond to a single attosecond pulse that in the frequency domain has a very broad emission, which indeed has no energy selectivity, but a very nice temporal structure. So nowadays, there are several attosecond sources that have been developed, covering mostly the VUV region, but also the soft X-ray region is now accessible with attosecond sources with photon energies covering the whole water window, extending up to 500 eV and beyond. And the shortest attosecond pulses are in the order of few tenths of attoseconds. You can also find here a very nice review paper covering all the most recent technological developments on attosecond sources, which I will not have the time to cover in this lecture. So now we have this XUV attosecond pulses, but we want to use them for time-resolved measurements. As I was mentioning, this is an extremely nonlinear optical process, and therefore it has also a reduced conversion efficiency. So it's not easy to get high photon flux, at least not comparable as the photon flux you can obtain from free electron lasers. And therefore, we often don't split the XUV attosecond pulses in two arms to perform an XUV pump, XUV probe experiment, but we combine our XUV attosecond pulses, for instance, with a residual part of the IR laser, so that we have an XUV pump IR probe setup. Here you can see a typical interferometer. This is completely developed in vacuum, as the XUV light needs to be transported in vacuum. And you can see here also the typical characteristics of those pulses. So in our case, we generate attosecond pulses covering a spectral range up to 40 eV, and we combine them with sub 4 femtosecond infrared or near infrared pulses for our experiments. And the duration of our attosecond pulses is in the order of few hundreds attoseconds. Now, using this technology, our goal was to try to investigate it, as I said, get access to ultrafast electronic mechanisms. And in particular, my group has been involved in various activities in this direction, but today I would like to focus with one specific investigation, which is the investigation of a charge migration occurring in molecules. Charge migration has been at first only theoretically predicted by the group of Lenz Sederbaum at first, and then other groups, including Françoise Remacle, indicating that after a sudden ionization or excitation of a relatively large molecule, in fact, you can create a non-stationary charge density distribution. And non-stationary means that the electronic charge will start to move very rapidly in the molecular backbone, even before the nuclei have the time to rearrange. Here is a sketch of this mechanism where you can see a calculation performed in a small peptide. An electron is suddenly removed, and then you see that the charge density distribution is not static, but as I said, rapidly evolving. You can see the charges going from one side to another of the molecular backbone within a few femtoseconds. And this can also happen within a few hundreds of attoseconds, depending on the energy separation between the electronic states. In fact, what you need to do is to create a superposition of electronic states, and this can be done either by ionizing an electronic correlated state, which is by definition a superposition of states, or by using a broadband laser pulse, which is intrinsically creating a coherent superposition of electronic states. This process, as I said, occurs very rapidly, and so we need attosecond or few femtosecond light sources to get access to it. And it has attracted our attention, as we know electrons are playing a major role for the creation of bonds or the cleavage of bonds, and therefore the main question was, can we use these ultra-fast mechanisms to ultimately control the reactivity of the molecule? Or in other words, can we achieve a charge-directed reactivity? So the way we approached this problem was actually to implement a relatively simple experiment at first. And we studied the photofragmentation in a time-resolved manner of aromatic amino acids. In this case, this is the amino acid phenylalanine, which are the nano-sized antenna of our proteins, as they can capture very efficiently light. And here we were sending a sequence of an XUV attosecond pulse, followed by a few femtosecond infrared pulse, as I was describing before. And in fact, after ionization, the molecule fragments in many pieces, and you can measure with the detector the mass spectrum as a function of the delay between the two pulses. This is the typical fragmentation of the molecule. So you have a high level of fragmentation with several fragments, as the deposition of energy is relatively high. And in this very rich mass spectrum, we have been interested in a very small fragment, in fact, the doubly charged ammonium ion. And by tracking the mass of this fragment as a function of the delay between the two pulses, we could clearly identify rapid oscillations, as you can see here, in fact, happening within a few femtoseconds, both for the phenylalanine amino acid at first, and then later on in another experiment in the tryptophan amino acid. Now, those oscillations were too fast to be assigned to any of the vibrational motion of the molecules, and therefore we collaborated with our theory partners at that time, Fernando Martin from Universidad Autónoma de Madrid, to find an interpretation or to find an explanation for those fast oscillations, whether this was a signature of the charge migration. And indeed, we could finally understand that that was a signature of charge migration, and in fact, those oscillations could be assigned to the migration of the charge from the amino group to the carboxylic group of the molecule and back, occurring on a 0.25 petahertz scale, so few femtoseconds. Same was for the amino acid tryptophan that was analyzed later on, and here the frequency that we observed in the experiment was the result of the interference between two oscillatory dynamics, one from the amino group to the ammonium group of the molecule and back, and the other one again between the ammonium and the carboxylic group of the molecule. That was very fascinating, and we then therefore decided to investigate other molecules which are biorelevant, or again building blocks of our big biomolecules. In this case, DNA building blocks. We studied adenine. As we know, again, damage of the DNA can occur both for exposure to UV light, but also to high energy photons or even secondary electrons created by high energy radiation propagating in the human tissue. And in this case, the deposition of energy, for instance, during phototherapy treatments, is in the order of 20-30 eV, so exactly the energy that we have available with our photon sources. So we were looking already at the photostability of the molecule when exposed to such an amount of energy. And again, you can see that the mass spectrum reported here show a high level of fragmentation, about 80% are fragments, as expected. And again, we were looking at the mass spectrum of adenine when launching IR probe pulse after the XUV photoionization. And there we could clearly see that, in fact, when you look at the palm probe signal, this is the integrated mass of each individual fragment. In fact, the larger fragments are drastically reduced at 0 time delay. So when we send the infrared pulse synchronized with XUV pulse, and the smaller fragments are increasing. And this is basically due to the fact that we deposit a further amount of energy using our infrared laser on top of the XUV pulse. And this is bringing the molecule to further excited states that ultimately leads to a higher level of fragmentation. However, a very interesting observation back then was the presence of the detection of a stable molecule. So this is the intact adenine molecule, doubly charged, which is not showing up when we send the near pulse synchronized with the XUV pulse, but only 2.3 femtoseconds afterwards. So we need to wait for a very short time before we can observe the creation of such a stable and intact adenine molecule. And this time, again, it's too short to basically hidden or to basically have behind a structural reorganization of the molecule. So we were looking again for an electronic mechanism to explain this sort of stabilization mechanism of the molecule, which otherwise undergoes photofragmentation. And here we came up with this simple explanation in collaboration with our theory collaborators again, the group of Angel Rubio this time from the Max Planck Institute of the Structural Dynamics here in Hamburg. In fact, after the ionization from our XUV pulse, we have an electronic process happening, and this is due to the correlation of the states and the fact that an electron is rapidly filling this vacancy by promoting a second one to the outer valence. This shake-up mechanism, in fact, allows us to have an electron available now in the outer valence for our probe, near infrared probe pulse, to be ionized and therefore create this stable and intact adenine. Now, the interesting aspect here, in fact, is that theory predicts that during this shake-up mechanism, which is again due to the fact that we create a superposition of states by ionizing a correlated state, we don't have a static charge density distribution, but we have a migration. And the migration in this case is an out-of-plane inflation of the charge. So here you can see that the charge is in fact rapidly inflating, and this inflation is responsible for an increased absorption of our IR probe pulse, which otherwise would not occur. But we need to wait around 2 femtoseconds before this inflation is effective and in fact allows us to absorb the infrared probe pulse. So this is just an example how we can use the charge migration mechanism to obtain a new outcome for the molecule, in this case, the stabilization of a molecule which otherwise would be photofragmenting after the exposure to UV light. I showed you examples of the study of charge migration in photoionized molecules, and this inevitably happens every time we use VUV or XUV light, as this is above the ionization potential of all the molecules. And this radiation is in fact very interesting, but not representing, of course, the majority of the phenomena which are happening on Earth. As we know, ionizing radiation is not penetrating our atmosphere. And a very interesting wavelength is, of course, the UV photon energy or UV light, as it's responsible of many photoactivated mechanisms. We have seen before, I gave you the example of the photo-induced damage or recovery, but also UV or visible light is very interesting for optimizing light harvesting and getting, of course, energy out of the solar light. So what was the effort of my group in the last few years was actually to push the attosecond technology forward and in fact combine our attosecond pulses with UV light. And in fact, we wanted to preserve the temporal resolution of our, so to say, experimental setups by generating extremely short UV pulses. And in order to do that, we have been exploiting the third harmonic generation in gas. We have designed special gas cells in glass via a laser micromachining of glass in order to confine the gas efficiently over a few millimeters. And these special gas cells, which allow basically to achieve very high pressures with an optimal gas confinement, allowed us in fact to reach the sub 2 femtosecond regime for the generation of the UV pulses, and this has been published in 2019. In fact, back then was the world record for the shortest UV pulses ever generated. Now I want to provide you an example where we can use these ultra-broadband UV pulses, in fact, to initiate charge migration in a special class of molecule, in fact, to control their functionality at the electron time scale. This class of molecules are chiral molecules, and I would like first to briefly introduce the concept of chirality. As many of you know, chiral objects are non-superimposable mirror images, one of the other, and the easiest example, of course, is our ends. And in the case of chiral molecules, the two enantiomers, this is how they are defined, they have the very same chemical composition, but being one mirror image of the other, they have very different chemical functionalities. And for instance, all the living organisms are mostly dominated by one of the two enantiomers, for instance, the L amino acids, and therefore homochirality has emerged, so to say, in life. And in the field of pharmacology, chirality is very important because a molecule that has an healing effect for our body has a corresponding enantiomer that has a very toxic effect. For instance, the case of methamphetamine is the most popular, where L-methamphetamine is a very popular nasal decongestant, while the D-methamphetamine is a very dangerous drug. So chiral recognition is in fact a very important topic, and in our case, we didn't want to really work on implementing or introducing new chiral recognition techniques, but in fact to look at the chiral response of molecules when electron dynamics is activated. But in order to do that, we need to exploit a method to look at the chiral response of the molecule. There are different methods. One method is to the most so to say popular method is to let the chiral molecule interact with another chiral object, for instance, circularly polarized light. And for instance, one can have a look to the circular dichroism, which is the differential absorption of light when it's left or right circularly polarized. And this is actually quite a weak signal, as it is based on interactions between the electric and the magnetic dipole transitions. There is another effective method which has been introduced, which is the photoelectron circular dichroism. And here you use circularly polarized light to ionize a chiral molecule. And here, by keeping the same molecule but changing the polarization of light from right to left, you can see that the photoemission is happening forward in one case and backward in the other case. So looking at the asymmetry in the photoemission, one can detect the chiral response of a molecule. In our case, we were studying methyl lactate, which is a derivative of the lactic acid. So it's a molecule which is very important for our muscle metabolism and also has quite a high ionization potential. Therefore, it's very difficult to ionize it, as we wanted to prevent ionization of the molecule, but simply excite this coherent superposition of states using our broadband UV pulse. So here you can see the very broadband nature of our UV radiation, and we use a two-photon transition to excite a coherent superposition of Rydberg states. Afterwards, we use a circularly polarized infrared field to probe the chiral response, and we need only one photon transition to go above the ionization threshold and produce a photoelectron. So here is the sketch of the experimental setup. We can see a sequence of UV, linearly polarized exciting pulses and circularly polarized probe pulses, both with a very short duration. And then we looked at the electrons this time, not the ions, emitted after the ionization from the IR probe pulse. If you look at the angular momentum distribution of these photoelectrons, you can find quite a boring map. The interesting things come when you calculate the PECD, which is the difference between the circularly left polarized measurement with the circularly right polarized measurement. And here you can clearly see the emergence of the asymmetry I was mentioning before. So if this is the laser propagation axis, you can see that for one enantiomer, the emission is mostly backward, and for the other enantiomer, the emission is mostly forward. So we can clearly detect the presence of chiral molecules. But now these are static measurements, so nothing fancy. The fancy thing starts when we look at the time resolved measurements. So we look at the effect of the electron dynamics. And now we can see that, in fact, the PECD is changing very rapidly in a scale of a few femtoseconds. You can see that, in fact, we change the emission in certain energy regions from backward to forward, backward and forward again. So we can really switch the chiral response by looking at the evolution in time. You can do a more quantitative analysis, analyze via the Legendre polynomial and extract the beta parameters. This is a bit technical, but in fact, what you extract is again an oscillatory dynamics in the PCD. This is extracted for various kinetic energy ranges of the photoelectrons, and we can clearly see a beating frequency and the switch off the sign that has been observed in the PCD. Finally, theory helped us again in understanding the role of the electronic coherences. We could, in fact, via a collaboration with Bernard Pons from CELIA, see that with our UV pulse, indeed, we create different coherences. The 3D 4P coherence is responsible for the beating in the low kinetic energy region of our electron spectrum, while the 4P 4D coherence, which is created in the molecule, is responsible for the oscillatory dynamics in the high kinetic energy regions. These coherences are in fact activating the charge migration, so the electron dynamics, which is ultimately modulating the chiral response. So the message here is that we could see a completely switching sign over the chiral response of the molecule to chiral light without switching enantiomer on the electron time scale. So to just conclude and give you some take-home message, so to say, we can generate nowadays light pulses which are as short as few tenths of attoseconds. Attosecond pulses are now routinely produced with tabletop sources, as I was showing to you. But of course, X-FELs are also progressing very rapidly, and now attosecond pulses are available also at free electron lasers, and I'm pushing attosecond science towards the X-ray domain. We can track pure electron dynamics or charge migration in relatively complex molecules, and I showed you that we could take advantage of the electron dynamics to control certain molecular functionalities, for instance, the chiral response, which ultimately could lead to a charge-directed reactivity. With that, I would like to thank you. Of course, all my group, these are all the students who contributed to this work. You can visit our website to see our other activities, and thank you very much for your attention. I'm now ready for questions.
Thank you, Francesca, for this nice vision of what you can do on very fast pulses in attosecond and charge migration. We have a question from the web, and the question reads, do you think that the attosecond pulses can get much shorter than tenths of attosecond already achieved? Would shorter pulses open up new research areas?
Yeah, thank you for the question. Of course, we try to challenge ourselves always to go to shorter pulse durations. As I was saying, there are intrinsical limitations with the carrier wavelengths. So, of course, to achieve shorter pulses, you can, for instance, push towards other X-rays, for instance. And in fact, at the free electron laser facilities, there are very interesting perspectives in single spike operation. And by increasing the photon energy, we could achieve very short pulses, but also with the very broadband emission, now there are indications from theory that if you cover a very broad spectral range, you can also shrink the duration towards the septosecond domain. Although, of course, we lose energy resolution, as I was mentioning before. At the same time, of course, there are fastest mechanisms that one could address if you look into the nucleonic motion, as I was mentioning. So that would be an entirely new physics, and yet to see whether we can really get there.
Oh, okay, thanks for this question. I have a more philosophical question by myself about chirality. Yeah. I think there is a lot of discussion about the source of chirality. Did you thought about the possibility to just to take a molecule and to fragment the molecule and then to test if you can transfer chirality via light or chemistry to the fragment?
Yeah. Yeah, exactly. That's an interesting question. Actually, indeed, one has to see what refers to as a source of chirality, whether this is entirely due to the molecular structure, and therefore, if in this photofragmentation mechanism there is a residual signature of the chiral response. In our case, we are really interested into the, as I said, the interaction with another chiral object, which is in this case chiral light, and it's entirely a dipolar interaction. And therefore, we are very selective, as I said, with the electron dynamics. But a higher level of selectivity can be achieved, for instance, when we selectively excite chiral states. And therefore, for instance, we use chiral light for the excitation. So that go closer a bit to what you're saying, that we could, for instance, excite these electron dynamics using chiral light, for instance, with angular momentum beams or circularly polarized light, more simpler, and then see how this transfers to the dissociation of the molecule, for instance, and see if that has an effect in the further dissociation.
Okay, thank you. I think it's time to move to the next speaker. Thank you again, Francesca, for your participation and for your nice talk.
Thank you.
So the next speaker will be Professor Hervoye, I hope I pronounced correctly your name, Petek. And Professor Petek is at the moment is at the University of Pittsburgh in the US and is leading the laboratory of ultra-fast dynamics. His main research interest is on surface femtochemistry and photocatalysis and ultra-fast microscopy of coherent excitation. Please, Hervoye.
Okay, thank you very much. It's Hervoye Petek.
Hervoye.
I come from Zagreb, so not too far away from where you are.
Yeah.
And anyway, I would like to tell you about topological plasmonics on nanofemtoscale. So, as you all know, light propagates at 300 nanometers per femtosecond. And we would like to be able to take movies of light on such a space-time scale. And to do that, there's nothing faster than light, but we can rely on nonlinear effects to detect optical and plasmonic fields on such a space-time scale. So what I want to tell you in particular is how we can tie light into knots, such as suggested by this Escher image. And you can see that this image is chiral. And so we will make chiral plasmonic fields and detect how these fields propagate in space and time. So the work was started by my student Yanan Dai. He graduated. Atari Ghosh is a graduate student about to graduate. Sena Yang is a postdoc, and Jikang Zhu is another student working on this project. And Robin Huang introduced us to the topic of plasmonic vortices. So I want to tell you about topological quasiparticles. So our quasiparticles are of electromagnetic fields, but such quasiparticles exist in different aspects of physics, and they were first described by Tony Scrime in 1962, where he was describing surfaces of constant baryon density in nuclei, and he was trying to describe atomic nuclei solitons of light meson fields. Now, these topological structures have not been detected, and maybe with zeptosecond spectroscopy, one might be able to image such fields in atomic nuclei. However, such fields are more common, and they have been observed in vectorial magnetization textures, where they form skyrmion or meron magnetization textures, where the magnetization points up at the center of the particle or down, and undergoes a pi phase shift to the barrier. So this is a skyrmion, which has a topological charge of 1, and they can also be meron magnetization textures, where the spin goes from vertical to horizontal, and it has a topological charge of 1/2. So the merons are often called half skyrmions, because if you put two merons together, you get a skyrmion. Okay, and such field and spin textures have been discovered first in atomic nuclei, but they have been observed in ferromagnetic materials, where these magnetization distributions are stable quasiparticle on nanometer spatial scales. They exist in ferroelectrics. They have been discovered in Bose-Einstein condensates. And I will talk about vectorial optical fields, So we had a talk by Professor Capasso, which discussed structured light, and I'm going to show you how such fields exist in plasmonic materials in 2 dimensions. So this shows you a surface plasmon polariton field, so this shows a single cycle of such field, and the arrows show the electric field of such plasmons, which oscillate from being normal to the surface to being parallel to the surface. So the plasmons propagate at metal vacuum interface. They penetrate maybe 10 or 20 nanometers into the metal and few tens of nanometers into the vacuum. And we want to use such fields to change their topology and specifically to generate vectorial optical fields. And we want to image that. So we are going to image them by electron emission microscopy, which gives us nanometer spatial and femtosecond temporal scale. And I want to tell you about how we design such vortices by spin-orbit interaction of light. I will show you how we can generate various plasmonic vortices with spin textures and topology. And finally, I want to point out that only 5% of the universe responds to light, and the remaining 27% is dark matter. And we would like to use such vectorial fields to detect dark matter, and I will tell you how one might be able to do this. Okay, so I will be talking then about vectorial properties of optical or plasmonic vortices, and for this we are going to use the spin and the orbital angular momentum, and so you understand about the spin angular momentum, so you can generate circularly polarized light, which will have either spin of -12 or +1/2, and this will involve rotating polarization of the optical field. Optical fields can also have orbital angular momentum, and this involves rotating wavefronts. And these fields form scalar vortices. Now, if we combine the optical and spin angular momentum, we can make vector fields with different distributions. So this yellow donut shows the optical field distribution. There is a phase singularity at the center, so the field goes to 0, and the spin can circulate. It can have circular polarization, it can have linear polarization. It just depends on how you superimpose these momenta. So angular momentum is conserved as usual, and so we have some total angular momentum, which is orbital plus spin. And what we are interested in is imaging the spin-orbit interaction of light in space and time. And to do this, we use plasmonic fields, and we describe them by Maxwell's equations. And Maxwell's equations are extremely versatile. They will give you all of this, but there's something missing in these Maxwell's equations, which I will discuss. And so what we want to do is we want to use the full vectorial properties of light, so amplitude, phase, polarization, spin, and orbital angular momentum to tailor structured orbital fields, structured optical fields. So you all know about phase singularities if you have seen a tornado or a hurricane. At the center, there's a phase singularity, which causes the wind to stop, and on the outside it is circulating. And this circulating structure can traverse over continents because angular momentum is conserved. Okay, so what we are going to do is we are going to do ultrafast microscopy, and we are going to have two pulses which excite a metal surface. The two pulses can have circular or linear polarization, and they will excite a silver film. And to excite the surface plasma polariton, we need to provide momentum. So light cannot excite surface plasma polariton directly because there is a momentum mismatch, but we have a sharp structure, sharp on the optical wavelength scale, which generates angular, or it generates momentum so that surface plasmons can be excited and propagate into this film. And if we have circularly polarized light, there will be the K vector that is generated will have some phase delay as this light circulates around. And this surface plasma polariton will then be focused into the center of the circle. And what we detect is electrons which are emitted by nonlinear two-photon photoemission. And we image these electrons in order to determine the fields that we are generating in this metal film. So this metal film is going to have orbital angular momentum associated with this spin circulation of the excitation light. And it will form a vortex where the field is going to circulate into the center. So there's going to be orbital angular momentum. And plasmons also have spin angular momentum. So as I showed you, the electric field circulates as surface plasma polariton propagates, and this creates a spin angular momentum, which is transverse to the propagation of the plasmonic field. So this is the K vector of light that we generate, and we will have spin angular momentum pointing in this direction if the K vector is in this direction. If we now reverse the K vector, the spin angular momentum is going to point in the opposite direction. So these surface plasma polariton fields are chiral, and you can calculate the spin angular momentum from this real and imaginary cross product of the K vector. Okay, so this is how we generate the spin-orbit interaction of light, and the way we image it is with a photoemission electron microscope. So we have a microscope which operates either as a low-energy electron microscope or photoemission electron microscope, and we excite the surface with a pulse pair normal to the surface. And this pulse pair is going to generate electron emission normal to the surface, which will then propagate through electron optics, through aberration correction, and it will be detected with few nanometer spatial scale resolution. So this is a highly parallel detection. So we are detecting two space coordinates, and we are changing the time between the pump and probe pulses, so we can generate images of the photoemission as a function of delay between the two identical pump and probe pulses. So this is what the movie looks like. We scan the delay in about 50 to 100 attosecond intervals, and we generate images, and then we get images of the plasmonic fields forming a vortex, and the resolution is much better than the wavelength of light, and the time resolution of these images is determined by the delay scanning. So we generate a vortex, and this vortex will be a stable structure on the time scale of the optical pulse envelope. So this can be a continuous vortex, or it could be a few femtosecond vortex. It depends on the envelope of light. And this technique is described in a Chemical Reviews article from 3 years ago. So we had a visitor, Robin Huang. He came to our lab, and he knew about plasmonic vortices, and he introduced us into doing such research. So I want to tell you more about magnetoelectric interaction. You certainly know everything about electric dipole interaction, but we can use electric and magnetic fields to excite electric dipole and magnetic dipole interactions, and we can generate a superposition of such excitations in materials that have magnetoelectric response. So 150 years ago, Maxwell described his Maxwell equations, but as I said, they're not complete. So these are the usual equations that you know, but there are other terms that you can add where instead of just having electric field, you have a magnetic field that is acting as an electric field. And instead of just having a magnetic field, you have an electric field that is acting as a magnetic field. And so this is the magnetoelectric effect. There are some materials which have such response. And for this, you need another Maxwell equation. You have to add the fifth one, which is the axion law, where the E dot B term is a source of this theta field, and this theta field is the axion field, and kappa is the coupling between the electric and magnetic fields, and so this describes the magnetoelectric response of materials. Of course, in a propagating field in vacuum, this term is going to be zero, but in a plasmonic system, you can make this E dot B term to be dominant. So axion has been proposed some time ago as a particle that solves the charge conjugation parity problem in strong interactions in high energy physics, and later it was proposed as a candidate for dark matter. And so by generating these, so this E dot B field is a source of axion fields, theta, and we hope to be able to eventually use such fields to detect axion dark matter. Now, okay, so I'll share some results. Now, in this case, we are going to use linearly polarized light, which is a superposition of left and right circularly polarized light. And we're going to generate optical or plasmonic angular momentum using an Archimedean spiral. So this spiral has a radius that changes by pi as you go around by pi. And this is going to create an optical angular momentum for the left and right circularly polarized fields. And it will generate a vortex which has a phase singularity at the center. Now, to explain how we do these experiments, I show you the entire image that the microscope sees. And so this is a photoelectron image of the fields that are excited in the sample. And the pump pulse is going to interact with the structure that generates surface plasma polaritons, and it will send surface plasma polaritons to the center. And this will propagate at 300 nanometers per femtosecond. Now, to detect this motion, this is the field created by one pulse. So this field comes to focus, and there's some interferences. This is due to interferences between the optical field that generates the pulse and the propagating pulse, plasma pulse. And also there's interference between light that comes from the opposite direction. Now, to image the fields, what we do is we send in a second phase-correlated pulse, and we generate interference between the plasma wave and this optical field, which is oscillating parallel to the surface. And so this is a movie that we can generate for this structure. But this movie has a contribution from time-evolving fields and stationary fields. And we use Fourier analysis to separate such fields. And so after Fourier analysis, we can show that we have a plasmonic vortex, which each one of these red regions corresponds to one cycle of light, or a plasmon, and the field is propagating in this direction on the top, in this direction on the bottom, and you can see that there is a vortex motion with a phase singularity in the center. So this is experiment and simulation. Okay, so we are using then coherent spectroscopy and microscopy, and we use phase between these two identical fields. The polarization is defined. It generates orbital angular momentum, and we generate spin-orbit interaction of light. And then the question is, where does the angular momentum go? It has to be conserved. And I would claim that the angular momentum must be in the photoelectrons that we detect. We have not imaged that yet. Okay, so this is the movie that I showed you, and after Fourier filtering, then we can show how these fields form a vortex, and they are oscillating on femtosecond time scale, and we are imaging them on nanometer spatial scale. Now, we have three-dimensional imaging, two spatial dimensions and one time dimension. And we can extract further information from this. This is called optical flow analysis, where we extract how fast do these fields evolve. And from the optical flow analysis, we can get information on subdiffraction spatial scale. This is imaging of about 50 nanometer spatial scale, which shows where the field is propagating the fastest. And where it's propagating the fastest is where it's linearly polarized. Where it's propagating the slowest, it is circularly polarized. And this is a calculation of the linear and circular polarization. So we call this the L-line map. When the field is linearly polarized, then the spin is in the surface plane. When it's circularly polarized, it is above the plane or below the plane. So this gives us the spin distribution of our plasmonic field on few tens of a nanometer and femtosecond time scale. And from this, we can conclude that the spin texture looks like this. So at the center, the spin is pointing up for the circular polarization. And at the edge, where we have this L line, it is pointing in plane. And from this spin texture, we can conclude that this field consists of 3 Meron structures. So each one of these structures has a topological charge of 1/2. So this is a Meron structure. Okay, so I'm telling you about polarization of light or polarization of surface plasma polaritons on nanometer scale. And so I told you that we can image where the plasma is linearly polarized and where it's circularly polarized. And so these structures are called L lines and C points. So light is propagating first at L lines and it's circulating in space at C points. And L lines tend to be connected and C points tend to be isolated points. Okay, so we can quantify this on a Poincare sphere. So Poincare sphere is a three-dimensional plot of the Stokes parameters of a field. And so the Stokes parameters are shown here. The north and south poles correspond to circular polarization of the light, and the equator corresponds to the linear polarization of light. So Professor Capasso showed a similar image, and so what we're interested in is to use the Poincare sphere to determine what is the topological charge of the field that we are generating. And the topological charge is defined in this way. This is a function of the normalized spin. And the question is, how does this normalized spin cover this Poincare sphere? And if only 1/2 of the Poincare sphere is covered, so if the polarization goes from linear to circular, then we have a Meron or topological charge of 1/2 or 1/2 Skyrmion spin texture. Now, if the spin texture covers the whole sphere, then we have topological charge of 1, and we have a Skyrmion spin texture. Okay, and we have played with these coupling structures and linear and circular polarizations of light to generate various plasmonic field distributions. And so this shows a progression from a triangular structure to square structure, pentagonal structure, and so on. And as we increase the number of sides of this structure, we converge to something that evolves into a circle. So this would be an infinite number of sides of this coupling structure. And so we're interested in the topological charge, how it evolves as we go around here. And what I want to tell you about specifically is the circular structure. So I told you about the Meron structure, but a circular structure generates a Skyrmion spin texture. And so we have a circular structure, 2 circularly polarized pulses exciting, and what we image in the microscope is this. Now we are interfering the in-plane field with the surface plasma polariton, so we can determine the in-plane field, and this side of this image is 2 lambda, so we are getting the distribution of the radial field on sub-diffraction limited spatial scale. We can use this field and Maxwell's equations to determine the surface normal field component. This has a topological charge, so it has a singularity at the center, so the phase in the center is undefined and the field strength goes to 0 at the center. So this is going to be important. And then we can also determine the angular spatial distribution. We can determine where the K vector is, or where the field is linearly polarized. And so we are determining distribution of the K vector on deep sub-diffraction limited scale here. And this gives us, this tells us where the spin is in plane, and in the center, the circulation is circulating, so the spin is up, and at the edge, we have it changes by pi, so we have a singularity here, and so if we calculate the topological charge within this region, we get that the topological charge is 1. So this is the red line is experimental measurement, the dashed line is a calculation, and we see as we go from the center, we have 1 skyrmion of topological charge of 1, and then we have another skyrmion, and so on. So from this, we get the spin texture of our plasmonic field. Now we can go further, and we want to address the magnetoelectric effect inside plasmonic vortices. So we can, for a material with a magnetoelectric response, we can write the D field and the B field in the following way. So it's a combination of electric field and magnetic field, and the B field is combination of magnetic field and the electric field, and we have these coupling constants, and so depending on whether, so for a normal material like silver that we're using, these coupling constants will be 0, and so we will have a simple isotropic medium, which we're making anisotropic by the plasmonic field. And then if these quantities are nonlinear, we can have a telogen medium, which is a magnetoelectric medium, or a Pasteur medium, which is a chiral medium. And so this is a bi-anisotropic material, which has it's asymmetric with respect to parity and time symmetry, but its PT symmetry is symmetric. Now, if we look at the plasmonic fields at the center of the vortex, the yellow line is the E field, the blue line is B field, and what you see is that at the center of a plasmonic vortex, these fields are parallel, and this shows the angle between the two fields over one optical cycle, and the angle rotates, but in the center it is always parallel. So there is a magnetoelectric response in the center. And so these parallel fields have non-zero EB driving term, which interacts with matter unlike optical fields, and the magnetoelectric response, which can excite the axion field, is present here, and such fields can interact with topological materials, for example, and they're thought to interact with the axion or dark matter. Okay, so the last thing I want to show you is that we can image this magnetoelectric response. And so I showed you that we have these components of the field. The Z field has a phase singularity. We can also calculate the H fields. So there is the eye of the plasmonic vortex with the phase singularity, but these other fields have the maximum at the center of the vortex. And so we can also determine the spin of these fields. What is most important is we can determine what is the E dot B distribution within this center. And so it has a focus which is about 0.29 times the wavelength of the plasmon at the center. So the magnetoelectric response is focused in the center, and one can obtain a parameter which is magnetoelectric density. So this is where the electric and magnetic or magnetoelectric response is stronger than the dielectric response of a material. And this experimentally is focused to 74 nanometers. And this is a time-independent quantity because the field is circulating around this area. This is something I should have erased. So this magnetoelectric response we can find in all of the vortex systems. So they form arrays which are focused to within about 10 nanometers, and we plan to use that to study magnetoelectric response in topological materials. So the idea is to do point-care engineering, and this is to use light-matter interaction of vectorial fields to detect axion fields in the near-field region. So by placing a topological material next to plasmonic material, we hope to detect axion fields in solid state. Okay, so what I have shown is that ultrafast microscopy is capable of detecting synthetic axion response in various materials, and we eventually hope to be able to use such fields to detect cosmological axion matter or dark matter. And okay, so this was done within my group. Yanan Dai, who is now in China, Southern University of Science and Technology, he's starting this sort of research there. So he was the main person for the Skyrmion research. This is now continued by Sena Yang and Ataria Ghosh. And Ataria Ghosh is going to be graduating. She's a very illustrious student. And this is my current group. And Chen Bin Wang taught us about vortices. Thank you very much.
So, thank you very much, Hervoy. We are quite late, so probably we have to skip question and go to the next speaker because we are already half an hour late. That doesn't matter anyway. So it was very interesting, and thank you very much for your talk. So let's move now to the in-house speaker. one should be Daniele Trucchi from Diatema Lab, talking about all the materials that are preparing and that can be used to make light. Please, Daniele.
Thank you, Lorenzo. I will make a short overview of the activities of the Diatema Lab involving the light, since today is the day of light. Diatema is the acronym of Diamond, Thermal and Harsh Environment Materials and Applications. The labs are located in the Monte Breti section of Institute of Structural Matter, close to Rome. And let's start by speaking about the facilities. We assembled the facilities in order to complete the chain from production of materials to characterization of their chemical physical properties with spectroscopy techniques, microscopy techniques, and so on. After that, technological processes for device fabrication, because we would like to demonstrate physical principles and new devices at a prototype scale, and all the techniques for characterization of device performance, depending on the device, from climatic chamber to vacuum and temperature electronic characterization, solar furnace, X-ray photoconductivity setup, and so on. Plus, there is the Tempism, the platform of ISM, completing the techniques both for synthesis, analysis, prototyping, and so on, for the development of materials and devices. Let's start with the electromagnetic spectrum, from radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, in order to think about how the light is used. Let's start with advanced treatments and the characterization of materials, which are in the visible, a part of the infrared, in collaboration with the Femtolab of Potenza, Tonino Sant'Agata presented the activities. We uses ultra-short laser pulses for making treatments of material with enhanced resolution due to reduced thermal effects, to the capability of treating transparent materials thanks to multiphotonic effects, and also the formation of surface periodic structures which modify significantly the optical and electronic properties of materials. We developed materials such as black diamond, that is simply a material with a periodic structure on the surface, which depends on the material refractive index and on the laser wavelength. For example, we use also light for Raman spectroscopy, in this case in the visible, to characterize the materials. We are able to, with the ultra short laser pulses, so not only wavelength but also the time scale, for modeling the materials and changing its the profiles and introducing defects, optical and electronic defects. This is an example of black diamond with a pseudo two-dimensional periodic structure, and this is the indium phosphide with a very good periodic structures, which we are studying. Let's go to electromagnetic spectrum in application, high temperature solar energy converter. So we are using visible light plus a part of infrared and a small part of ultraviolet. We would like to develop converters for solar concentrated systems, which are less expensive than distributed photovoltaics. They can reach high temperature, they can co-generate energy, they are compatible with thermal energy storage systems with innovative technology like fermionic based conversion. The first one is the more mature solar fermionic thermoelectric generator, and the other one is less mature but in principle more performing at a lower temperature, high temperature solar cells based on photon enhanced fermionic emission. We develop the materials, we engineer the device, and we demonstrated the prototype, the first prototype of this kind of converter. Also, photon-enhanced fermionic energy converters, in principle, they interact directly with the radiation to produce photoelectrons and photoholes. This is the band structure in a defected semiconductor like black diamond. The important thing is that we demonstrated the theoretical approach reported by the Stanford group, which introduced the concept, and we demonstrated it with a black diamond photocathode. Let's go further with the electromagnetic spectrum. Let's move a bit to the infrared. So we are developing thermal energy converters from high temperature sources, specifically ultra based on thermophotovoltaic conversion. The temperature is very high. The concept is to store at high temperature heat in a source, and after that exploding both electrons and photons that can be emitted from this hot source. And we are developing cathode and anode with a lower function. We published it in ACS Energy Letters. Let's analyze electromagnetic spectrum again. Laser beam converters for space application, because there is a demand from space application to transfer wireless the power. So laser beams are ideal because for their ability to concentrate the power density. And for example, one application could be the missions on the moon. And we are using this the photon-enhanced fermionic energy converters also in this case, because they can work well at high power densities and at high temperature, and as well as they are lightweight for space applications. Let's analyze again the electromagnetic spectrum. We are developing quantum optoelectronic platforms by providing the key enabling with femter and like LEDs, waveguides, electric contacts to be merged together into a three-dimensional integrated optoelectronic platform able to manage quantum signals. Again, electromagnetic spectrum. Let's move to higher energy radiation, UV and X-ray photodetectors. Diamond, we have got an experience with diamond UV detectors, X-ray detectors, and we are extending it to neutron spectroscopy for nuclear fusion in ITER. And also we are working in gallium oxide films on the electric in collaboration with IMEM of Parma. The latest development are about perovskite detectors, which can be imaging detectors in surgery, radioprotection, and radiotherapy, for the development of tools able to be used in surgery by surgery operators. And perovskite is the election material because it is a low production. It has a low production cost. It can be deposited on large area, on curved and flexible substrates, and it can support photovoltaic operations. The Atema Lab is in it and work seriously every day to make such results. I thank all the collaborations inside and the spectroscopy lab in ISM, but also several groups in other institutes and other research centers. Okay, very much. And I would like to start a presentation and a movie representing a bit the results involving light with the Diatema Lab. If the organizer could make it run. Okay. Okay. The mic, Lorenzo.
Sorry. Okay, thank you, Daniele, for your presentation.
Thank you,
and to stay on time. And let's move to the last presentation of the day that is presented by Roberta Totani and concerns the activity of ISM at Elettra. Please, Roberta.
Hello, everyone. Thanks, Lorenzo, for the introduction. I would like to start with a short video just to show you what the Institute of Structure of Matter does at Elettra, the Italian synchrotron facility. So I would like to ask the organizers to start the video, please. Okay, so I would like to start my presentation now. I can start sharing the screen. Can you hear my screen? Can you see my screen?
Yeah. Yes. Yes,
okay.
We can.
Perfect.
Go in presentation mode. Okay.
Okay. So after this, after the short introductory video, I would like to tell you a little bit more about synchrotrons, how a synchrotron about how a synchrotron works and about its beamlines. So at this point of the day, I hope this is not going to be too boring or too obvious for you. But if you're not that into synchrotrons and particle accelerator in general, probably you might have two legitimate questions: what is a synchrotron and what is a beamline? Plus some other, plus some other questions, such as, for example, what do synchrotrons have to do with light, and why are they brought into play when in occasion of the International Day of Light? How does light is produced, and what is light used for? So I work at Elettra, which is the Italian synchrotron facility, which is so in Trieste, not far from the sea, but on the Carso Plateau. A synchrotron is this building here, which has this donut shape, and is basically a big microscope allowing to study the structure of matter. Allowing to study the behavior of atoms and molecules, how they behave on their own, how they interact with each other. And this is possible thanks to synchrotron light, which is produced by ultra-fast electrons traveling at almost light speed, and whose trajectory is deviated with a proper system of magnets, and in doing so they lose energy by emitting the so-called synchrotron radiation. Or synchrotron light. But of course, I'm not speaking about traditional light, as it's not light, for example, emitted from a lamp or a bulb, or not even sunlight, because synchrotron light is a billion times brighter than the sunlight and brighter than any other traditional light source that we might know. So in order to answer the second question now, what is a beamline? Then let me tell you a little bit more about synchrotrons and how they work. So this is Elettra seen from the top, and you might be able to see two main structures, one main ring and a smaller structure inside it. Now, what would you see if you were able to take a look inside? Well, for sure, you would see the electron source, or as it is called, the electron gun, which is a small metal disc with hundreds of volts applied, emitting electrons, which are further accelerated inside this small ring, which is called booster. And afterwards, they enter the main ring, which is called the storage ring. And here, their trajectory, their path is deviated by these complex and proper systems of magnets. And they lose electrons by emitting synchrotron radiation. So here is where synchrotron radiation is generated. And afterwards, this radiation, or as it is also called the photon beam, is channeled along these straight structures here, which are called beamlines, and which transport the photon beams from the storage ring to the place where experiments and measurements actually occur, which are the experimental stations, where synchrotron light or photon beams interacts with samples. There are a total of 28 beamlines at Elettra, located in this place that we call experimental hall. As you can see, of the 28 beamlines, a consistent numbers is run by CNR, and the other beamlines are run by collaborations with foreign research facilities and universities. Among the CNR beamlines, there are 3 beamlines which are completely which are run by the Institute of Structure of Matter: VUV photoemission, circular polarization, and gas phase. So this is from this picture you can see how the experimental hole looks from the inside. Here you can partially see the circular polarization beamline, and you can easily guess where the storage ring is located, which is right behind this brown LED panel. This is an image of the circular polarization beamline from the ground floor, and here you can clearly distinguish the beamline, which is this straight structure here made of optical components such as mirrors and gratings, and which are connected to each other by a system of stainless steel tubes. So the optical components have the task of not only of focusing the photon beam, but also to monochromatize it, meaning to select a specific photon energy or a range of photon energies according to the experiment and the measurements that we need and we want to perform. And photon beams travel from the storage ring, which is located here, up to the experimental station at the end, right at the end of the beamline. You can have different experimental techniques available at the synchrotron, depending on the characteristic of the photon beam, of the range of the photon beam, that usually can go from the ultraviolet rays passing through the soft X-rays and up to the hard X-rays. According to the characteristic of the samples, to the characteristic of the end stations, to the geometry of the end station, and to the detector that we want to use. And you can apply these techniques to literally a huge variety of fields to perform experiments, for example, of science and fundamental research regarding new technologies and future materials, the environment and alternative energies, medical research and structural biology, but also archaeology and cultural heritage. So, for example, you can perform some astrophysics and some astrochemistry measurements if you want to investigate highly charged ions, meaning ions that completely or almost completely lost their electrons because of high energetic collisions or because of the interaction with high energy photons. And so this is actually, even if it might look a little bit odd, this is actually the predominant form of matter in universe, because this is how matter is found in and around stars, in galaxies, and even in the intergalactic medium. Realizing and performing high resolution measurements of highly charged ions is fundamental if you want to have a deeper knowledge and understanding of the universe, and if you want to solve well-known open question in astrophysics, like for example the missing baryon issue. But in order to do so, you first need to produce the highly charged ions, and this is done. For example, this is doable if you have an EBIT, meaning an electron beam ion trap, a particular device able to first produce and then trap and confine and control these highly charged ions. So this is what has been done at the gas phase beamline, where an EBIT was moved from the Heidelberg Max Planck Institute in Germany and mounted and installed at the gas phase beamline. And then their scientists were able to exploit the high resolution offered from the beamline in order to really obtain high precision measurements of highly charged ions of nitrogen and oxygen gases. But synchrotron radiation can also be applied to study and develop new technologies and future materials. For example, at the VUV beamline, a two-dimensional material obtained exploiting the surface the self-assembly of this bromine-based molecule was studied and characterized. So VUV beamline is specialized in performing in studying the band structure of materials, and in this case, the band structure that could be measured revealed the presence not only of Dirac cone, but also of flat bands. And these are all very convenient properties for two-dimensional materials, and which might be implemented in fields such as, for example, electronics or photonics. So these results are very promising for future implementation in these fields of this kind of material. However, synchrotron radiation can be also used if we want to unveil Stradivari's secrets in realizing its famous instruments. For example, at the CC beamline, a sub-millimetric sample taken from a very famous Stradivari violin could be examined and analyzed by a combination of infrared spectroscopy and nanomicroscopy techniques, and also exploiting the very convenient high spectral and spatial resolution guaranteed by the synchrotron light. In this way, scientists were able to prove the existence of a proteinaceous layer that Stradivari supposedly used as a further protection for wood. So this layer is located between wood and external paint, and could be the responsible for the unique sound characterizing these very precious instruments. And synchrotron radiation turned out to be also a very useful diagnostic tool in medical research, as it was exploited at the CIRMAP beamline of Elettra in order to realize some phase contrast breast tomography, which revealed to be totally equivalent to the image obtained with traditional method, as, for example, you can see from the comparison with an histology image acquired by using a traditional optical microscopy. But even more, synchrotron radiation, since synchrotron radiation can guarantee a much more enhanced contrast in the acquisition of images, it can also furnish much more information with respect to a traditional mammography. For example, you can see here from these pictures, this is the comparison between a traditional mammography acquired at the university hospital and phase contrast synchrotron radiation mammography. And you can see that the structure here indicated by this white arrow, which is a 5 millimeter Benning sized, is definitely much more visible in the image acquired with synchrotron radiation with respect to the image obtained with traditional mammography. So to conclude, we have here at Elettra this huge, roughly 80 meters diameter storage ring, where ultrafast electrons are traveling almost at light speed, over 1 million of times per second. And this is in an ultra bright light source, which is exploited by 28 beamlines to realize cutting-edge research in different fields, going from astrophysics to biology, from nanotechnologies to archaeology and cultural heritage. And if we manage to do all this with Elettra, with the old synchrotron, we cannot wait to see what is going to happen with Elettra 2.0, which is the upgrade of the current machine, which is going to be realized in a few years from now. And of course, with MOST, which is the new beamline, which is going to take the place of the already existing circular polarization and gas phase beamlines. So we are looking forward to the future challenges and future scientific discoveries that all this will bring to us. But in the meanwhile, I would just like to thank you for your kind attention.
Thank you, Roberta, for your presentation and for presenting the different activity at Elettra and the possibility that exists on the application of the Elettra to a lot of fields. So I think that we are coming to the end of the day. We have seen today during the symposium the different facets of light from the different sources with different wavelength and a different pulse duration, the application to material, different material, the technology that help to control, manipulate the light, and also how to investigate the deep fundamental property of the light, like the quantum aspect. So it seems that, as one of the speakers said, that the application of the different light sources to the investigation of matter, to the understanding of matter, has quite a brilliant future. So on behalf of all the colleagues of ISM, I will thank all the speakers that have made this symposium very interesting and very active, and also all the people that has contributed to organize the symposium.